I think, okay. Hello, everyone. My name is Alan Yang. So welcome to the ISMAR 2022 tutorial. Our tutorial title is OpenArc, Tackling Augmented Reality Challenges via Open Source Software Development Kit. We have been offering this tutorial for the past 3 times, but not consecutively because of the pandemic. As you are going to see here that we have much updates from the last times that we have offered similar discussion here. And also I want to share this, the Zoom link, actually the website to you. We have pre-recorded our tutorials, and then the videos are online on our website, vivecenter.berkeley.edu/tutorials. If there's any network issues, we hope that you still get the full presentation from our website. All right. So with me is my colleague, I should say former colleague, Adam Chang, and then together with Mohammed Kashavasi. So he is still in transit to Singapore. He wanted to attend in person. He tried his best, but due to visa issues, he's going to be late for just 1 day. So today's tutorial is going to be hosted by me and Adam together, and we're happy to answer any questions that you may have. You can participate online, or we can answer your questions after each of the sessions. Okay. All right. So let me start the first one first. Okay. So make sure that I also share my computer sound, right? Okay. Okay, here we go. Thank you. Hello, everyone. Welcome to ISMAR 2022 tutorial entitled OpenArc, Tackling Augmented Reality Challenges via an Open Source Software Development Kit. My name is Alan Yang from the University of California at Berkeley. Before we start today's tutorial, let me introduce our contributors for this tutorial. I'm currently the Executive Director at the FHL Vive Center for Enhanced Reality at the Berkeley in the Department of EECS, and I was formerly the Chief Scientist at the Fung Institute, also at the UC Berkeley. And our second contributor for the tutorial, Dr. Mohammed Kashavasi, he received his PhD degree from Berkeley Department of Architecture and also from the Vive Center. He was formerly a generative design software developer from the Autodesk and also was a researcher at the Facebook Reality Lab. Our third contributor, Adam Chang, he was a lead undergraduate developer from Berkeley for the OpenArc project, and after his graduation, he's currently working at the Wall Street. Since part of our research was supported by the Vive Center, and we are going to make our slides and the video presentations available on our website, vivecenter.berkeley.edu. And then you should be able to find those files shortly after this tutorial. So now let me start the first part of the tutorial to give a general introduction of the topics we're going to talk about. So I choose the title of my talk to be The True Cost to Blur Reality and Virtuality. Understand the fundamental challenges in creating virtual 3D experience. I would always like to start my talk about AR/VR using a short motivation video from Steven Spielberg's 2018 movie called Ready Player One. I'm sure that many of you have watched this movie. It claims to be the first Hollywood feature presentation based entirely on the background of a dystopia VR world. Since this is the first, it makes a lot of our consumers today believe that a future of AR, VR, and the metaverse applications will look like this.
First to the key.
First to the egg.
Turn AR/VR may have become a household name today, but I think the public may be still surprised to learn that the first prototype of AR/VR was invented by Morton Heilig in 1960 and 1962 with the two groundbreaking inventions. One is called stereoscopic television apparatus for individual use, and the second one is called the Sensoroma. In these inventions, Heilig already stipulated that for personal consumption of 3D content, a wearable headset needs to be manufactured, which contains two small displays, although at that time the invention used the old CRT tubes for the display. But after the small pictures are passed through a lens group, its field of view will be drastically increased, and its focal plane will be properly projected somewhere in front of the human eyes. Another thing that Heilig paid special attention, which you only got to experience today in the Disneyland and the Universal Studio, is the use of wind and the smell to create a sense of reality. For example, in Sensorama, when the 3D movie showed that you driving down the street of Brooklyn, you could feel the vibration of the uneven street from the chair and then the motorcycle handles. At the same time, the machine will stimulate the smell of the street of Brooklyn. In 1968, of course, Ivan Sutherland further created the first prototype of wearable AR headset, which used prism, or the so-called half mirror, to merge the images from the side displays and the images from the front physical environment. Because the optical was so heavy at that time, it needed to be hung from a hanger from the ceiling so as not to crush your nose bridge when you worn it. After 60 years, if we look at the four major system form factors today, many of them still bear the same virtual reality modalities from their original inventions. From the biggest to the smallest, first we have the elaborately created simulation environments. These include flight simulators from the airplane manufacturers or VR escape rooms games you could find from many major cities in the US. Many of the first-gen models from Oculus or HTC Vive are tethered to PCs, a signature feature that indicated that you have a tethered VR device is that you have a long cable running from the head mount to a stationary PC, which clearly sacrifices the modality. The experience of these first-gen consumer devices could also be horrible if you have too much mobility, whereby you may hit your TV, furniture, or even your loved ones with your fist or your 3D controllers because you couldn't see them in VR. There are endless versions of these accidents on YouTube, so therefore today I'm not going to show them. This brings us to the next form factor, all-in-one wearables. These are considered to be the holy grail of AR/VR experiences, such as HoloLens. In some industrial and military use cases, you can imagine that maintaining a user's peripheral vision is very important, regardless whether you are seeing a virtual world or a physical world from your wearable. Another advantage of all-in-one is mobility. You literally carry the entire computer system on your head. Of course, the current drawbacks of all-in-one wearables are also mainly twofold. Number one, the cost of putting all the AR/VR components on your head to wear is still very expensive. Second, the weight is also substantial. For the record, the heaviest pair of sunglasses that a human wearer can tolerate should be below the 200 gram, while the HoloLens 2 currently double that number. But almost everyone has a smartphone today. So if we want to further reduce the cost of wearable AR/VR experiences, some smartphone companies such as Apple and Google are offering a set of AR library such as the AR Kit or AR Core to enable mobile AR experience directly on their smartphones. Today, when we compare the four form factors, we may compare based on these metrics: cost, visual fidelity, motion tracking, and the user input. For the first two form factors, if the cost is not a concern, today's technology can already create highly vivid AR/VR experiences. If you don't believe it, just go to Disneyland this weekend. But for our research, I believe that many technology gaps still exist that hinder the adoption of the last two form factors. Arguably, the last two form factors are the ones that consumer can afford to eventually purchase. So, therefore today, we will discuss these topics on perception and the UI/UX tasks for low-cost, all-in-one applications. First, many of our AR/VR users should be noticed that as soon as you don an AR/VR headset, the virtual information is beaming to your eyes from three interactive spaces, so to speak. User interaction with the information presented from these three spaces presents a very different set of challenges. Next, let us first separate our discussion based on the three spaces. The first space is what I call the near-eye display space, or the NDS. Typically, in an AR headset, NDS is used to render 2D menu or items on head-mounted displays. For example, Google Glass with a single see-around display setting only has the NDS and does not have the other two spaces we will mention later. Content displayed on NDS typically is not anchored with any physical objects, and the triggering interaction with this content only has limited interaction methods. For example, with eye tracking, with the voice, or with 2D touch on the device to navigate through up, down, left, or right motions, like controlling a game controller. Finally, NDS is often reserved for displaying private information. Therefore, the content is rarely shared between different users on their NDS space. Next, within an arm's reach, we have the egocentric user space, or the EUS. As its name suggests, EUS is an immersive virtual space with its origin anchored from the user's own perspective, and typically will move with the user's movement. Think of this as a 3D version of a Zoom call you can hold to carry on your laptop. Typically, user interaction in the EUS is projected within an arm's reach from users, say, 1 to 2 meters away. Within this distance, as the image on the left-hand side shows, the most obvious input method are hand gestures and the 3D controller. Content on the EUS is typically not shared, unless you borrow from the example of a Zoom call, where you can deliberately hit the share button to let other people see your share screen. Even in this case, the content could be shared. Each user usually sees only an individual version of the shared data. Otherwise, think about the counter example that instead of you seeing your hand grabbing a virtual shopping cart or virtual object in front of you, a third person could extend a virtual hand to manipulate virtual objects in front of you. That could be a quite scary movie experience. The best place to create a shared working space or shared playground is in the overlaid world space, or the OWS. For this purpose, OWS models and coincides with the physical world. Many AR systems must be able to model and keep track of the physical world, such as HoloLens or the ARKit. More importantly, interacting with the OWS content implies interacting with the real world, such as the example shown on the left. If a family of 3 or 4 are playing a virtual board game on a table, then each user must interact with the virtual content at the same time that they interact with the physical table and the physical space around the table. And the origin of OWS is usually anchored at a fixed 3D location. Typically does not change also with respect to users' movement around the anchor. Therefore, in multi-user applications, an OWS and its content can be shared and manipulated by multiple users. For example, on the left, having multiple users to reach out to play the same game together will be a very natural and pleasant user experience. To summarize the pros and cons of the 3 interactive spaces. For NDS, any content should be anchored on some fixed display coordinate, because literally it serves as a regular 2D display function. A user can use voice, gaze, or 2D touch to navigate, but multi-user sharing is very rare. For the EUS, its content is anchored egocentrically, within an arm's reach from the user. It is convenient to interact with the content using either natural hand gesture or 3D controllers. But at this space, multi-user sharing is still very rare and not common. Finally, for the OWS, content typically is rendered based on a world coordinate origin. Interacting with the world with the OWS implies interacting with the physical objects and its environment. So therefore, multi-user sharing in this space could be a very popular option for the applications. So based on these separation of 3 spaces, today we will go over selected technical challenges to really bring us to the Ready Player One future AR/VR experience, namely to finally blur reality and the virtuality. So the challenges we're going to talk about today, for display technologies, I would like to highlight some of the challenges to produce retina display for AR/VR experiences. For interaction technologies, I would like to highlight perception tasks for creating egocentric 3D UI. In the OWS space, we will focus on technologies that will enable seamless content sharing across multiple users and many environments, including SLAM, digital twin, contextual spatial computing, and I will touch lightly about decentralized privacy issues. First up, what is the technology cost to create retina near-eye display for mobile AR/VR? We know that retina display was coined by Apple as a marketing jargon, essentially emphasizing the fact that when display technology can depict discrete pixels more than 60 pixels per degree viewing angle, then the human eye will perceive a continuous picture instead of perceiving the so-called screen door effect of discrete pixels. Now, let's calculate. Let's assume that the first generation retina display on the iPhone 4 generation has 960 pixels on the long side. Then 960 divided by 60 ppd will be equal to 16 degrees. So our calculation tells us that a 960 resolution display could be qualified as a retina display, but only conditioned on the fact that we must see the entire screen of 960 pixels within 16 degrees. Now let's look at the situation for near-eye display. Our human eye normally perceives 160 degree FOV horizontally or 175 degrees vertically. Now compared to the previous 16 degree, you can immediately see the problem. We need a huge number of pixels to qualify to create a retina display at the 160 degree field of view. We can forego some peripheral vision and focus only on the overlapping areas between the two eyes to create stereo vision. Over here, we still have 120 degree field of view. What that means is that for a retina display to cover the stereo near eye display area, at the minimum, we need about 60 megapixels, which is equivalent to a 8K display or TV today. Remember, that calculation still only cover for one eye. For two eyes, we will need a dual 8K resolution, dual monitors. This is just the bare minimum. Think about this is the configuration corresponding to the first generation of iPhone 4. As we always want to upgrade the displayed technology, such as we are upgrading the iPhone from generation 4 to generation 14 today. Any future upgrade of the retina near eye display could lead to a more ideal resolution at the dual 16K. At this resolution today, we don't even have a commercial big screen TV to match that resolution. Now, having that many pixels is only half of the equation. We also need to transfer data to display on the dual 8K pictures continuously, ideally at the 60 Hz. Again, if we just calculate the lower end of streaming single 8K video in compressed format, we could need 5 gigabit per second. So this is wider than any typical gigafiber internet service for the household today in the US. So this is a task we will need to put to our communication companies to generate these technologies and services to qualify to create the retina near eye display. 5 years ago, when working for a Silicon Valley startup called Lucy, I led a project to create the first prototype 4K dual micro OLED near eye display. On the left is the design rendering, created working closely with a top industry design firm at San Francisco. Right out of the bat, you can see that the headset is quite large because there's no way to hide that when you shrink the display to the micro OLED size while maintaining a large field of view, you will need to increase the size of the lens group. There's really no free lunch. But we wanted to hide its large form factor by shaping it like a pillow, which conveyed the perception of familiarity and the feather lightweight. In fact, at that time, the codename of this device was the pillow. On the right, let me play a short video of the CES 2018 show report about the Lucy Alex. As far as I know, Alex is the first 4K micro OLED display to be deployed at a CES demo. And the many news articles after reviewing this demo device has high praise about the beautiful aesthetics of the device.
Now onto a recap of some of the action coming out of this year's Consumer Electronics Show. As Zoe Richards reports, people are still talking about two new wearable technologies recently revealed at CES. Here's a look.
At the Consumer Electronics Show in Las Vegas, two amazing products were unveiled. The new Lucy Immersion on-demand virtual reality headsets. Lucy Immerse and Alex by Lucy are one of the most ultra HD wearable technology that boasts the most immersive 3D and 4K entertainment experiences available.
Next up, let's take a look at our options for egocentric 3D user input. In this category, there are three clear categories: using 3D controllers, using hand tracking, or using full body tracking. Now, for research purposes, of course, we wanted to write papers about hand tracking and full body tracking. But I will be the first to caution our users that if the speed and low latency is a major concern, then using controllers is still the best option for our users. Now, today, due to the interest of time, we will not spend much time on hand tracking solutions because hand tracking can be considered a mature technology. But overall, we still need to be aware of the three approaches for providing hand tracking. First is using depth camera, such as myself created a gesture recognition system for another startup called Athere in 2012. I had about 10 patents contributing to Athere's portfolio. If you wear HoloLens, you will notice that the first generation of HoloLens used camera-based modality to provide hand gesture tracking. Finally, there are dedicated hand gesture sensors produced by various companies, such as the Soli from Google, and there is another very famous sensor solution called the Leap Motion, also designed from the Silicon Valley. But personally, I still prefer the depth cameras because none of the other solutions can support hand gesture to manipulate 3D virtual objects directly from their absolute 3D coordinates. In Berkeley's open source OpenArc library, we also provide a solution for depth-based full body avatar tracking. Next, let me play a demo video. Our former student, Bill Zhou, created this video. In this video, a single Intel RealSense depth camera was used, and the algorithm behind the demo video was beyond the scope of today's topic, and please refer to our open source project for its implementation on the GitHub.
In this demo, we will show a model-based, fully deformable human avatar reconstruction system based on a single RGBD camera view. This will be available as a module in OpenArc, which will help AR devices better understand the human body and its interactions with other real-world objects. We begin with a linear low-dimensional model of the human body called a symbol. The model consists of joints and shape keys which can adapt to any body type. Given a single RGBD observation, we attempt to fit a parameterized model to the depth image. The model-based tracking allows us to infer missing points.
Gangnam Style. Oppan Gangnam Style. Gangnam Style. Oppan Gangnam Style. Hey, sexy lady. Oppan Gangnam Style. Hey, sexy lady.
As you can see from the demo, the extraction of the 3D simple model from the RealSense depth camera is quite noisy. In fact, that was the main challenge for almost all depth cameras, even more so for earlier generations, such as PrimeSense, acquired by Apple, Softikinetic, acquired by Sony, and the PMD. The average depth air signal could be as much as 10% from the distance of the object. And almost all early generation of the depth cameras also did not work well outdoors. Right now, for consumers and researchers, we have a much better range of advanced depth camera to choose from, such as the Stereolab Z2 camera, Microsoft Asia Kinect camera, and on every iPhone Pro, the current generation, we have a LiDAR camera on the back. There are overall 4 different technologies that will support the manufacture of depth cameras, primarily used for consumer products. Due to the interest of time, I'm not going to go over the pros and cons of these depth cameras. Interested readers can refer to our slides for more details in this topic. But I do want to show you in this presentation some visual comparison, emphasizing that different technologies do lead to very drastic differences in the result of the depth. This is a study that's sponsored by one of our industrial sponsors, Ford, to study how to put AR/VR experiences in the future autonomous vehicles. At Berkeley, we have tried to install depth cameras to activate some basic 3D perception functions, such as gesture recognition, face recognition, etc. On the left, I will first play a result returned from an Intel RealSense D435i camera. It used the depth from stereo technology. And the video shows me driving my car in a typical urban environment with the different sunlight and the different vegetation background. And then I'm going to play the same route being captured by the Microsoft Azure Kinect sensor. Now for Microsoft Azure Kinect, it uses the time of flight technology. Hopefully from these two videos, you can draw the conclusion yourself about the different depth camera technologies and its effect to the final depth result. The availability of accurate depth is equally critical for room-size 3D hologram applications. In here, I will recommend two demos from Microsoft Holoportation Project and the Google Project Starline. But due to interest of time, I will highly recommend that you can appreciate their proposed technology advancement from their demo videos online. Inferring depth is also important for solving 3D localization, which reveals where you are when you are navigating in the physical world and the virtual world concurrently. In here, I'm going to show you a Pokemon Go AR experience to illustrate the use of 3D localization in a AR experience.
Oh yes! Watch out, guys! Hello, heads up!
Actually, the initial Pokemon Go AR experience could only be called a weak AR experience because the 3D localization was solved only using the GPS signal, which gives only a rough X, Y, Z coordinate up to several meters air. For more accurate 3D localization for both X, Y, Z, and also the orientation alpha, beta, gamma for 6-degree freedom, up to centimeter accuracy, we have an open source implementation in OpenArc to provide the so-called visual inertial odometry. Next, let me show you a demo video. Imagine somewhere near the origin of the world, we place a virtual cube. this virtual cube can be equivalent to a monster in the Pokemon Go AR experience. And then our researcher is going to walk around and come back to the original space and check on whether the same virtual cube is still at the location initially being placed. And that is the 3D visual inertial odometry demonstration. Of course, visual inertial odometry is not the only way to offer precise 3D localization. There are three primary approaches. The first one is called outside-in, which is similar to localization using GPS satellites. More generally, if you have set up some base stations that can provide periodic signals where you may scan for their timing and strength on your device, then you may infer your own localization based on the technology called triangulation. Oftentimes, triangulation, after an accurate calibration, merely takes the time complexity to search in a lookup table. So therefore, it is very cheap. But it also comes with its baggage, that the environment needs to be instrumented, and it does not work if the user walks out of the limited space. The second approach is visual inertial odometry. The best engineering practice will need dual cameras and an IMU. More importantly, every sensor must be synchronized based on a common clock. This approach is widely used in many all-in-one wearable AR/VR systems and the mobile smartphone to AR experience. The third approach, a recent approach, is called the digital twin localization. In here, we can use camera, IMU, and the LiDAR measurements, but its assumption is different. Digital twin localization will assume our training algorithm can be learned based on a set of known objects and their digital cat models. For inside-out localization, typically it solves both localization and the mapping simultaneously. Hence, there's another name for that called simultaneous localization and mapping, SLAM. It typically does not use deep learning, but multiple geometry to solve for the rotation parameters R and the translation parameters T, based on the current real-time frame and some stored keyframes in the history. Our OpenR solution, similar to many state-of-the-art solutions, comes with well-known limitations. First, hardware sync between sensors is a must. If you lost time sync between the sampling stages, it is very difficult to get it back because of the ambiguities of the timing. Second, for SLAM, dual camera setup is always better than a single camera setup. Third, more is not always better. What I mean by that is that some of you may be surprised to learn that many matured SLAM algorithms by design excluded using the depth sensor. Conversely, some depth-first cameras such as Asia Kinect did not come natively with a slant capability, but rely on some third-party implementations. Fourth, less is also not always better. When we don't have depth, SLAM may fail when 3D surface that an RGB camera sees lack visual features. So this is easy to see on the left, that if we started tracking a clear white wall, then we will have no visual features to track. Over time, the localization result will drift away randomly from previous keyframes. More recently, we collaborated with our industrial partners at the Vive Center to work on a different type of localization problem called digital twin localization. We have not released the public code in our OpenR GitHub yet, but we plan to do so by the end of this year or early next year. But in our experiment, we have seen very encouraging results that we can reduce the 3D localization error to sub-centimeter accuracy. So let me play a demo video from our project team this year.
Hi, this is Team Digital Twin. We're a part of OpenArc project. A digital twin is a virtual copy of a real-world object, system, or process which can simulate the behavior and condition of the represented item. The key problem in digital twin is 6 degrees of freedom post-estimation that identifies the real-world object's rotation and translation. We designed a symmetry-aware post-estimation model that aims for real-time post-estimation tasks with sub-centimeter accuracy, and we achieved 11 frames per second on a 1080 Ti GPU. We visualize our model's performance via a simple augmentation test, where we place a 3D text above a target object. For example, here we set the can as our target object and place a white 3D text object above the target can. We can see that the 3D text moves according to the movement of the camera, but the relative position and rotation between the 3D text and the target object stay almost the same.
Next, let's discuss spatial computing that merges virtual and physical world. For this part, I will largely do a quick highlight to advertise Mohammed's PhD dissertation published this year and draw the selected results from his papers co-authored by me and his advisor Luisa Caldas from the UC Berkeley. And of course, Mohammed is going to discuss all these topics in more detail in his section of the tutorial. The simplest question we may start asking is the problem of asset placement across different platforms. Now, this problem is related to the term responsive display design for websites in Web 2.0. With the websites we are viewing across different platforms from desktop, tablets, and smartphones every day. More specifically, imagine you are a web developer. Before, it is straightforward to write a piece of HTML file to fire up a standard website for PC. But now, you need your website to be properly deployed and viewed across multiple platforms, including with the possible different OS, different smartphones, and any other possible forms in between. These unknown rendering terminals bring challenges to your website design because a website that is not coded to cross-platforms cannot be displayed properly on desktop, tablets, or phones at the same time. This is the problem for Java, HTML, and the so-called CSS scripts to solve. However, we also need to recognize that although web designers for 2D needs to accommodate different device sizes, resolutions, and their orientation, at the least, within the 2D viewing area in a browser app, its UI functionality is uniform. We do not have separate viewing areas for very different interaction and computing purposes. Now, when we carry over the same asset placement problem for 3D AR, our future metaverse developers will face even harder challenges. Namely, when a metaverse experience is being coded, the developer will have no idea what the eventual 3D layout of the spaces such experience will be consumed. Furthermore, if we're talking about consumer applications, our users may immerse in metaverse from very different spaces with the different contextual functions. For example, when we are in a company office, we may have a company layout. When we are in a hospital, we will have a hospital bed and other medical devices. And while when we are in our own home, we could have a living room with a sofa, big TV, and even a fireplace. So clearly, our future metaverse developers will be faced with more challenges to deploy a quality 3D AR experience in one or more unknown spaces. Creating a multi-user AR experience is in fact more challenging than merely managing virtual assets. Our program also needs to manage unknown user input that may be completely out of the control of the program. To borrow the example of website layout problem, although a website layout needs to change with respect to different computing terminals, but at the least, the layout is not affected by the perspective angle of the user and shouldn't change based on different modalities of the interaction method, such as user using a keyboard or user using a 3D controller or the user using a mouse or touch screen. But in 3D AR, because virtual assets are co-located with the physical world and the real users, if unknown user input is not carefully managed, like the example from Muhammad's PhD dissertation highlighted, one person may perceive another user during a virtual interaction by talking into a wall, or perceive another user standing in the middle of their bed. These user placement mistakes will not conform to the expectation of everyday normal user, and oftentimes the scenario will be awkward. To find out our solutions discussed in a list of papers I listed here, please also make sure to check out Muhammad's tutorial session next. Lastly, I want to lightly touch a new issue of privacy we just started thinking about. Earlier, we have seen in Muhammad's wonderful algorithms that calculate the best placement of virtual asset and the best constraint for limiting the interaction of virtual users in physical spaces. But an underlying condition is that we or a company that enable this interaction and the user experiences need to be disclosed about your very private information, about your room and about yourself in order to perform the optimal optimization. This will raise a lot of privacy concerns. For example, it has been shown that if a central entity holds the private information about a user and or their spaces, other users may infer users' own private spaces. Other users may further infer a user's metadata. More dangerous is the case if bad actors get hold of such information, then they may create fraudulent counterparties to scam innocent users. But note that these challenges in safeguarding user privacy is not unique to Metaverse and the Web 3.0. Crimes of fraud or scam are as original as the invention of the telephone or the post office way before the internet, such as we receiving the robocall, or we could receive fake IRS letters asking us for money. The growth of the internet only makes safeguarding user privacy even more challenging. For example, there have been much discussion about how many bot users are infecting social media platforms, such as Twitter or YouTube. For high-profile political topics, you may be surprised or not surprised to learn that there could be as much as 50% of the conversations that have been generated by bots. In AI, it has been well known that DeepMind was famous in training their AlphaStar AI agent by playing against human players and while pretend to disguise their computer agent as another human contender. Much worse is the well-documented deepfake attack, which could hijack the likeness of famous people in order to promote scams online. This will bring to the conclusion of my talk today. We started looking at the Ready Player One as a model of AR/VR technologies, but actually, I think that what the story wanted to tell us is really about how to properly safeguard user privacy and encourage data decentralization. Now, to conclude, let's together will the ending of the movie.
This is wrong. This pen, this contract. This is the moment that Halliday made Morrow sign over his shares in Gregarious. That was the biggest mistake of his life. He knew that. This can't be the end. It's a test. I won't make the same mistake you did.
Oh, good. I just needed to be sure.
This is where you grew up.
Oh, that's just me, a long time ago. I like to have them around from time to time. Hey, I have to show you something. Come on. This is the button. If you push it, the whole simulation shuts down and a tapeworm program will erase all of the backup servers. So you now have the power to turn the Oasis off forever. You understand? Yeah, try not to accidentally erase the whole of the Oasis on your first.
So, how can Metaverse do a better job on privacy? I like what Mark Zuckerberg's view that Metaverse isn't a thing a company builds. It should be the next chapter of the internet overall. What does that mean? It means that compared to Web 1.0 and Web 2.0, in the Metaverse, users themselves should own their own data, and their data should be immutable. When we communicate with the third party, there should be a financial penalty built in that makes the cost of conducting fraud and scam more costly than any potential benefits of the scam themselves, or the so-called trust but verify strategy. Eventually, the entire Metaverse ecosystem should be decentralized and not controlled by a single private company. After all, this is what the internet is today, not owned by any single private entity, and the internet is by design interoperable. To open this new chapter at the Vive Center, we have created a Berkeley DeFi research initiative. If you're interested to discuss more about decentralization and interoperability in the Metaverse, please check out our website, defi.berkeley.edu, and much of what we are doing within the DeFi initiative is beyond the scope of our talk. But I would like to have a conversation with anyone who may be interested. All right, so this is the end of the first section of today's tutorial. Thank you very much. All right, thank you for listening to my talk. And before I hand it over to Adam, do we have any questions from the audience? Happy to answer a few. And also, I know that Adam from New York is already past midnight, so I'm eager to hand it over to him and let him to present his wonderful work while he's at Berkeley. Do we have a question? All right, so the host, if there's no question, so let me hand over to Adam.
Hi, can you guys hear me? Probably. Yeah, thanks, Alan. I'm Adam. I graduated from Berkeley this year with an undergraduate degree in computer science, and I work as a software engineer, kind of outside of the world of computer vision, but it was what I did for many years and something I'm very passionate about. Also, as Alan mentioned, it's quite late for me. So thankfully, I've pre-recorded a lot of my slides, and hopefully past me will do a better job than current me. And I will try to answer questions if anybody has any. Alan, would you mind playing my videos? Because I am not entirely sure if I have it set up correctly.
Right, so do you have a copy of your video? I think you can share a screen, or okay, I can play yours.
I can try it. I mean,
yeah,
because your presentation was just doing so well earlier with the audio and everything.
You can try, because I think that the video directly from you may be the best.
Okay. Or I would just play it off YouTube as well. So
Yeah, sure.
okay, well. Yeah, so I guess I'll just start it off.
Well, Adam, you have to share your computer sound.
Okay. Is that one of the options? Sorry. I see it.
Oh,
Share sound.
yeah.
Okay.
And then also just along the way, just click optimize for video.
Thank you.
Here we go.
Into three
Is this
key
better?
concepts in AR, VR, and Hi, welcome to OpenArc's ISMAR 2022 tutorial. My name's Adam, and today I'll be giving an introduction into three key concepts in AR, VR, and 3D computer vision: SLAM, 3D reconstruction, and digital twin. OpenArc is an open-source augmented reality SDK that will allow you to rapidly prototype AR applications. It was founded at UC Berkeley in 2016 with the mission of offering core AR functionality to developers for a multitude of devices. You can view our project website at the first link, and the source code is available at the second link to put to use in your own projects or contribute. On the right is a picture of my research partner Moonwan and I at the Jacobs Hall Berkeley Winter Design Showcase. Some of the core functions forming the foundation of AR/VR today are listed below. At OpenArc, we have developed and are currently developing systems to provide each of these functions. Today, I'll be focusing on three of the functions that OpenArc provides or aims to provide going forward: camera localization, 3D reconstruction, and 3D object tracking. First, SLAM. SLAM stands for simultaneous localization and mapping. Localization refers to the process of determining the current position of the camera with respect to some representation of the world. Mapping refers to the process of generating a representation of the world from a sequence of camera frames. These two problems are deeply intertwined. Some of the largest advances in industry AR/VR are powered by advances in SLAM. Of note are standalone VR headsets and in-picture AR mobile applications such as Google's 3D Object Viewer and Pokemon Go's AR Plus Pokemon capturing scene. What they share in common is the ability to anchor virtual objects into reality. This requires a frame-by-frame estimation of the camera's position at all times. The algorithm behind this is SLAM. Simultaneous localization and mapping, SLAM, is the computational problem of constructing or updating a map of an unknown environment while simultaneously keeping track of an agent's location within it. The GIF on this slide illustrates an example of a visual SLAM, which uses RGB and depth images from a video feed to track a camera's 6 degrees of freedom pose over time. The 6 degrees of freedom refer to XYZ position, pitch, roll, and yaw, rotation. Notice the yellow dots in the video feed. These are called key points, and they are vital to the operation of visual SLAM. In general, a SLAM framework is built with the following 4 steps. First, we initialize a map of landmarks. By landmarks, I'm referring to 3D key points and their associated features. Second, we receive a new key frame from the camera and estimate the change in position and rotation of this frame compared to a previous frame. Next, we extract the landmarks from this new frame and add them to our map. Finally, we optimize the pose estimation and optimize landmark positions in our entire map. This process can continue indefinitely, and the map continuously expands as new frames come in. So what are the building blocks of SLAM? Today, I'll be going over a few key building blocks that allow SLAM to work. First, key points and descriptors. Second, transformation estimations. Third, our map representation. Fourth, loop closure. And fifth, alternative sources of data, such as inertial measurement units. Key points, or features in the case of SLAM, are specific points in an image that satisfy these key conditions, allowing them to be used for SLAM. They are usually corners or pieces of patterns that can be identified and tracked with ease. They need to be salient, meaning they are unique points detectable from different positions and different image frames, and able to be matched between frames. This means that if I take an image of a building from one angle, reposition and take an image of the building from the same angle, I should be able to find key point pairs between the two frames. They need to be describable, meaning each key point needs a unique label. Creating this label is what transforms the point from a key point to a feature. One desirable quality is that the key points should be rotation and scale agnostic, as rotating the camera or moving further or closer from an object should not influence whether a key point is detected and matched to itself in a previous frame. Lastly, they need to be of relatively small quantity, as brute force key point matching requires n squared time, checking each key point in a new frame against every key point in a previous frame. Here are two examples of key point descriptors and descriptor extractors. On the left is SIFT, short for Scale Invariant Feature Transform. SIFT is an earlier form of scale and rotation invariant feature extraction, developed in 2004. It first detects potential key points using sliding windows of different scales. It then assigns an orientation to the key points based on a summary of the neighboring pixels. Finally, a feature descriptor is created from a 16 by 16 pixel area surrounding the key point. BRISC, otherwise known as Binary Robust Invariant Scalable Key Points, is a more recent algorithm, achieving competitive or sometimes better results, but with faster computation time. The image on the right depicts the sampling pattern that BRISC uses for generating a feature description. In their paper, they report a 3 times speed increase when finding correspondences between two images over older algorithms. Correspondence matching, being one of the most intensive portions of the SLAM algorithm, means this speed increase is greatly appreciated. Key point detection and description is one of the most important parts of SLAM, as they form the foundation of a SLAM algorithm's understanding of the environment. As such, part of this year's OpenArc team's work focused on testing different key point algorithms. We explored ORB, oriented fast and rotated brief, an improvement to an earlier key point named fast that incorporated multi-rotation and multi-scale components. We also explored some deep learning solutions such as R2D2, DISC, and Superpoint. However, we didn't find a compelling case for switching to deep learning features, as their performance gain was not definitive and the performance cost was very high. Once we have these key points, we can perform key point matching. Using correspondences between two different images, we can now move on to find the transformation between these two images. The next key concept required for SLAM is frame-to-frame pose estimation. Pose, or transformation estimation, refers to the relative translation and rotation between two image frames. The transformation estimation is performed using key point correspondences between any two frames. This is an optimization problem and can be solved in different ways. At its most basic level is the perspective and point algorithm, which, given a number of key point correspondences between two frames, can estimate the transformation between them. This algorithm, along with others, assume that the points recorded belong to a rigid body, meaning their relationship to one another in 3D space remains the same between frames. Another way to solve this frame-to-frame pose estimation problem is with an extended Kalman filter. By maintaining a state vector with all current observations and landmarks, the extended Kalman filter can be used to estimate the current position of the camera with minimal error. Once we have established these key points, or landmarks, we have to maintain some form of global map inside SLAM. One example implementation of this global map is a list of keyframes. Keyframes simply refer to images with their associated features and positions. Using these keyframes, we can perform loop closure when re-encountering a scene from an older frame. Another implementation of this global map is a list of circles. Circles, or surface elements, are small disks that dot the surfaces of objects in our scene. By using circles, we can also maintain a map of the scene that we've seen so far. The map is necessary for both estimating current poses as well as performing loop closures. What is loop closure? Loop closure seeks to answer the question, what happens when I come back to the same place I've been before? What do I mean by this? Imagine walking around a building. You start on the northwest corner of the building and slowly work your way around the building. Once you've completed the circle, you come back to where you began. However, Due to slam drift, which is inevitable due to noise, we find that our estimated trajectory takes us to a position different from our starting position. Loop closure refers to the algorithms that detect coming back to the same place, as well as being responsible for optimizing the camera's trajectory such that the current camera pose realigns with our start position. One such implementation of loop closure goes as follows. We maintain a map of keyframes and their descriptions. This description is called a bag of words. Then, with every new frame, we compare it to all previous frames and look for matches using these bags of words. If we detect a loop closure, we optimize the global map to match our new observation. The way frames are described is using a bag of words algorithm. The idea behind bag of words is to form a description of a frame using a vector of words. Then, the similarity between two frames is how many words two frames share in common. The words assigned to each frame are created using patches of the image. If two images contain a similar region inside of them, that similar region will be assigned the same word in both images, increasing the similarity between the images. The final part of loop closure involves optimizing the global map. One way of doing this is by iterating through a global map of keyframes and optimizing them one by one. We know the current frame's transformation to close the loop. We can then use the updated landmarks to calculate the optimization of the previous keyframe. We can continue to do this inductively until we have optimized our entire map. This procedure operates under the assumption that the detected key points or landmarks are where they were observed. Unfortunately, in reality, there is sensor noise that contributes to faulty key point observations. Bundle adjustment addresses this by not only globally optimizing the poses of the camera at each frame, but also the key point observations within them. Although more expensive, this often leads to more robust tracking. One final augmentation to SLAM is provided via alternative sources of data besides just visual, in this case, inertial. IMUs, or inertial measurement units, measure acceleration. One common place you can find them is inside your mobile phone, used for orientation measurement and other purposes. Inertial data is very helpful for our SLAM algorithm, as understanding the direction of acceleration more tightly bounds the transformation between two frames. Now that we have these fundamental building blocks of SLAM, we can see how they come together to form a fully fledged SLAM algorithm. In general, SLAM is broken into two parts, with the front end involved with tracking the pose of the camera in real time, and the back end optimizing the global map of landmarks. In code terms, these are two separate threads running side by side at different frequencies. Modern-day SLAM algorithms pick and choose a front end and a back end in order to achieve desired results of speed and accuracy. SLAM is an ongoing point of research, and several projects are striving to provide faster and more accurate pose estimation results. OrbSLAM 3 is one such open source project. It is a solely visual system with no inertial data used in its SLAM algorithm. BadSLAM features continuous bundle adjustment as its backend and differentiates itself from the others on the list by being a dense SLAM algorithm. Unlike a keyframe-based algorithm, BadSLAM keeps a map of each and every pixel and point observed by the camera, implemented as a list of circles. This results in a better performance in some conditions, but with heavier computational constraints, relying on a GPU to function in real time. OKViz features a visual inertial odometry system. This means that along with visual data, inertial data is used to perform SLAM. OpenArc SLAM system puts all these components together into a fully fledged SLAM system. It's built on several existing localization projects, OKViz, short for Open Keyframe Based Visual Inertial SLAM, and DLoop Detector, a loop closure detection library. It is capable of performing real-time frame estimations from a variety of different cameras, using RGB images, depth images, and IMU data to accurately generate its predictions. The underlying OKViz localization system uses a tightly coupled visual inertial odometry system for its pose estimations. The loop closures use the iterative keyframe method described earlier, where keyframes are optimized iteratively using key points and ransack. There are quite a few open source libraries that OpenArc builds upon to create the system we have today. First, as mentioned before, we have OKViz and D-loop detector, which form some of the foundations of OpenArc. Brisk is the key point extractor and descriptor used to featurize images. Eigen, series, and sweet sparse are all linear algebra solvers used throughout the system to solve optimization problems. OpenGL is used to visualize the result of the algorithm. debow2 provides the bag of words functionality for loop closure, and PCL, a point cloud library, provides functions such as the 2D to 3D projection and ransack PNP. There are many parts to pick and choose from when putting together a SLAM algorithm. Adding bundle adjustment results in higher overall tracking quality and tracking robustness at the cost of algorithm speed. Using a dense instead of sparse SLAM also potentially increases tracking quality at the cost of performance. With all these choices to make, it's important to understand the use case for your SLAM implementation. With so many parts to choose from, it's easy for a SLAM algorithm to begin losing efficiency to redundant data copies and transfers after incorporating too many different modules. This year's team at OpenArc focused on the code's efficiency. We removed inefficient and unnecessary data copies, resulting in a multiplicative speedup. Future work to OpenArc will likely focus on incorporating more of the SLAM functionality into our library and less reliance on open source libraries, a key step to increasing algorithm performance. To summarize SLAM, we have 3 steps that are performed continuously throughout the running of a SLAM application. A map of the environment in the form of keyframes and keypoints is constantly being added to and generated as more of the real scene is explored by our camera. The camera is localized at every frame within this map of the environment. And finally, loop closures are performed when returning to a previous point, re-optimizing the position of the camera and the map of the environment. The OpenArc SLAM team is constantly in flux as Masters of Engineering students come and go as the years go on. The lead graduate researcher behind OpenArc SLAM is Joseph Menke. The rest of the students listed here took part in developing OpenArc SLAM as part of their Masters of Engineering work in the last few years. Visit our website to see a full list of contributors to OpenArc as a whole. The final result is a SLAM demonstration where a set of 3 axes are anchored to the start position of the camera in 3D space, and the user is capable of placing objects at will throughout the scene, which will also remain anchored in 3D space, thanks to the estimation of the camera frame at all times. The code runs at 30 frames per second on PCs, laptops, and tablets. Alternative visualizations, such as bird's eye view trajectories, are also available. Coming up next, 3D reconstruction.
Yep, so that was the first part of my presentation, talking about SLAM, camera tracking. Are there any SLAM specific questions?
Oh, there's one hand.
Yes, hello.
Hey, so I had a question regarding the map representation which you use. So generally in SLAM systems, what happens is that once you add a point in the system, in the map, then yeah, the point does not get removed. Like say for example, if I was moving from one place and I scan a chair and then I move away from that place and then I come back and say if the chair was removed in between, then the map would not be updated to remove the chair points. But if the other thing had happened, like the chair was not there initially and I move further away and then I come back and then there was a chair, then those points would be added in the map. So like I have found that the removing these points from the map representations is particularly hard. So like does OpenArc system support like removing those map points or?
No, so our current implementation is using the traditional assumption that we are working in a static scene.
Okay, got it. Yeah, that answers my question.
The third part of my presentation is going to be about our current object tracking module. And this is like a solution towards your problem in terms of identifying individual objects, segmenting them as like an instance, and then recognizing when an object is removed from your scene. So separate from your static scene.
Got it. Yeah, that answers my question. Thanks so much.
So you can enhance your suggestion, your solution. Some typical solutions in doing localization and mapping in autonomous driving, for example, you can add a probability decay in your occupancy grid map. And if you add a probability model so that you allow the confidence of your occupancy to decay, then you can solve that problem. But it is up to you to add such a model. As Adam was saying, that our solution assumed a static environment that does not decay. All right, so Adam, let's continue.
Yep. Let me pull up the next video.
Now that we've built a foundation for SLAM, we can talk about 3D reconstruction. 3D reconstruction is the process of capturing the shape and appearance of a scene or object. 3D reconstructions can be created through a variety of different technologies. In the case of the reconstruction here, we used a sequence of RGB and depth images, estimated the relative poses using SLAM, and generated the 3D reconstruction by reprojecting the points from the images back to 3D space. In general, 3D reconstruction comprises of the following parts. First, you need some sort of point cloud data. This could come in the form of a sequence of RGB or depth images from a camera, or maybe 360-degree LiDAR data from a 3D scanner. Depending on the type of data, additional steps are required before any sort of 3D reconstruction can be extracted. For instance, given a sequence of RGB and depth images, steps have to be taken to find the relative position of all the images. Next, we need to perform integration, or merging the images together. Then we can perform mesh extraction, pulling out vertices and triangles from point cloud data. Finally, additional improvements can be made to the mesh, such as simplification or texturing. First, pose estimation. SLAM allows us to align the images into a common space such that we can integrate them successfully. We often refer to this common space as the world coordinate system. Once we know the position of a frame, we can combine it with all the other images we've collected so far into some data structure. Once we have a pose estimated image, we need to convert the depth image to a point cloud in 3D space. Assuming we're using a pinhole camera, we use the intrinsic matrix to project pixels from the image to 3D space. The intrinsic matrix is unique to each camera and is a projection matrix from a pixel on an image plane to a 3D ray. We then use the depth data to find the pixel's actual position in 3D space. Once we have these point clouds, we need a way to integrate them or merge them together. A naive way of doing this would be to simply combine them into a larger point cloud containing the points from both smaller point clouds. However, this loses the context in which these point clouds are generated. The points are noisy measurements of a common surface. Therefore, it is more effective to merge and average the observations of different frames to develop a better representation of the scene. We implement integration using a data structure called the truncated signed distance function, or TSDF. The TSDF operates as follows. First, we divide the space evenly into voxels, or volume pixels. You can think of them as small cubes. Next, we retrieve a pose estimated depth image and project its pixels into a 3D point cloud. These pixels all lie on the surface of objects. Depth measurements are taken of surfaces, and empty spaces have no observation. Next, for each point, we draw the ray from the camera to the point. For voxels along the ray before the observation point, we assign a positive value representing the distance to the measurement. For voxels along the ray after the observation point, we assign a negative value representing the distance past the observation. So this is inside the object. In this representation, when voxels change signs, this indicates a surface lies there. As we take more observations, we average out the values of the voxels. In this manner, we can minimize the impact of noisy measurements as each voxel value becomes the average of many different samples. Another benefit of TSDF is its performance. Integrating frames with one another happens extremely quickly, enabling real-time 3D reconstruction. Once the TSDF has been filled with observations, a mesh can be extracted. The predominant mesh extraction algorithm is called marching cubes. Marching cubes is an algorithm developed by Lawrenson and Klein in 1987 and uses the following technique to generate a mesh from a TSDF. For each voxel, we take the plus-minus value of each vertex, plus meaning outside an object and minus being inside an object, and perform a lookup based on the combination of the 8 vertices for the appropriate pre-computed mesh segment. There are only 2 to the power of 8, so 256, possible configurations for the vertices of a voxel, and many are rotations of others. The major benefit of using marching cubes is its speed, as it only requires 1 lookup per voxel and no other calculations. However, it results in a blocky texture, similar to that of Legos, due to the nature of the algorithm. This is counteracted by later steps of simplification, as well as increasing the resolution of the reconstruction. When simply generating a 3D reconstructed mesh, the complexity of the mesh becomes very large very quickly. For reference, this small section of my house, recreated on the left, has over 4 million faces. For comparison, this scene from Crysis 3, a AAA game title, has only 3 million triangles. The reason behind this is the existence of many small triangles that simply comprise larger triangles. This is due to the process in which our mesh was created. Each voxel, each small cube of space, generates anywhere from 0 to 5 triangles in our final mesh. Clearly, there is some redundancy there. For example, the wall of the hallway in the left image is basically a rectangle, just a rectangular plane in 3D space. This can be ideally represented by only 2 triangles. 2 techniques to reduce the complexity of a mesh are quadric edge collapse and planar extraction. Quadric edge collapse seeks to reduce the amount of faces in a mesh by removing edges and merging faces that reduce the error in the mesh the least. We do this iteratively, and this approach can extract a simpler mesh with minimal trade-off. For specialized cases, such as the hallway in the previous slide, planar extraction is a useful mesh simplification technique. The goal of planar extraction is to detect planes in a point cloud, and using this data, we can assign a few large triangles to represent an entire plane instead of millions of small triangles. Mesh texturing further optimizes the use of the mesh in applications, easing the process of rendering a mesh. Texturing is the process of mapping each point on the mesh to a 2D UV coordinate, and then saving the mesh colors instead of in the vertices themselves. Instead, we would save it to an image, a 2D plane to be used later. Although not relevant to real-time reconstruction, for incorporation of a mesh into a scene, texturing is very important, both for performance and high detailed texture information. Open3D, an open source 3D library, provides a texturing API for texturing meshes. One of the biggest hurdles to overcome in 3D reconstruction is the ability to perform the reconstruction in real time. With long computation times and endless memory, offline reconstruction is an art on its own and can be optimized to the point of perfection. However, in real-time 3D reconstruction, trade-offs have to be made for speed and memory efficiency. With real-time reconstruction, new frontiers of AR can be explored. One such application is HoloLens holoportation, Microsoft's technology that brings live 3D reconstructions of people into your living room via the HoloLens. An array of sensors takes measurements of one person, performs 3D reconstruction, and sends it to another person's HoloLens, allowing them to interact as if they were there. When dealing with real-time 3D reconstruction, we run into the issue of scalability. When performing offline reconstruction, once the data has already been collected in its entirety, the extent of the reconstructed scene can be calculated beforehand. During real-time 3D reconstruction, however, the system must be able to scale almost indefinitely. In order to achieve this, we performed several upgrades on naive TSDF. One major weakness of traditional TSDF is the issue of rigid space allocation. Because we divide the real scene into voxels of fixed side length, we must decide the overall dimensions of our scene upon the creation of the TSDF data structure, and many of these voxels will end up being empty because they represent empty space. One possible solution for this problem is a hashing function that assigns a value to sections of the real scene, each containing multiple voxels. This is called voxel hashing. Each one of these sections can be thought of as its own TSDF. In this way, the scene can grow dynamically as more parts of the scene are discovered and placed in the hash table. Also, parts of the scene that don't include surfaces won't be generated, so we can save space there as well. This allows a much more efficient and scalable TSDF representation. The implementation we use is derived from the elastic reconstruction system. Another solution to the scalability of TSDFs is mesh blocking, where every time the camera has moved a certain distance, a mesh is extracted and solidified, and the TSDF is reinitialized with the current camera position as its center. In this way, real-time reconstruction can be extended much longer. However, with the drawback that earlier sections of the mesh are now immutable. This also helps with speed, as the size of the TSDF we keep is limited, and we only need to perform minimal extraction. The attachment between blocks of mesh and keyframes is key to the speed increase and malleability of the real-time reconstruction pipeline. The rendering process of previous mesh blocks includes a step that checks each keyframe's position and location as estimated by the SLAM system and transforms the mesh appropriately. As we said before, loop closure can change camera poses from places we were in the past. As SLAM continually optimizes these poses and locations of past frames, the mesh blocks align more accurately with the real scene. In addition to the open source libraries required to run SLAM, which is also used during real-time 3D reconstruction, Open3D is another open source library used for OpenArc. The specific functionality provided by Open3D are the TSDF, or truncated sign distance function, the data structure used for integration of camera frames, mesh extraction, the implementation of Martian cubes, and voxel hashing, the spatial hashing function used to expand the scalability of TSDF. The SLAM dependencies are also listed here for convenience. One of the limitations of real-time reconstruction is the rapidly increasing computation complexity when the resolution of the mesh increases. For consideration, a room constructed at a resolution of 1 centimeter may have millions of triangles, while the same room reconstructed at a resolution of 3 centimeters will only have 10,000 triangles, a much more reasonable number to render and integrate to in real time. Also, in real time, optimizations to earlier portions of the mesh arising from loop closures are difficult to deal with, and oftentimes expensive operations are required, such as deintegration and reintegration of previous frames affected by pose optimizations. Therefore, OpenArc's 3D reconstruction module is broken up into two parts, an online and offline part. The online part runs real-time reconstruction at a lower resolution with the goal of providing the user a visualization of the current scanning process. The data is saved at the same time, and then the scene can be reconstructed at a very fine resolution once SLAM has stopped running and the poses have been finalized and optimized. The real-time 3D reconstruction demo has the following structure. As with the SLAM demo, first we initialize a camera object, specific to whichever camera we are using to run OpenArc. Then the SLAM system is initialized. Callback functions are passed into the SLAM system to combine both all the SLAM and 3D reconstruction maps. Then the main loop is run. When the output of SLAM is received and a pose has been estimated for a new frame, it is passed into the 3D reconstruction system for integration. It is also passed into the saving system for saving to be reconstructed later offline. Loop closures are also detected from the SLAM system, and the transformation of older mesh blocks inside the 3D reconstruction system are updated accordingly. The following screen captures are the results from our real-time 3D reconstruction algorithm. The code was run on a Microsoft Surface Pro, and the scene was captured in one cursory pass using a single RealSense D435i camera. The reconstruction required real-time integration, mesh extraction, and rendering. The data was also saved for later offline reconstruction. The integration was run at 10 Hz, and the mesh extraction was run at 1 Hz. One thing of note is that since the 3D reconstructions come from a single camera, gaps in the scene are inevitable, unless one is extremely careful about their scanning technique. Also, the back sides of objects in the scene will inevitably be incomplete as they are fully occluded. These screenshots here depict the difference between real-time and offline reconstruction quality. The image on the left, taken from a 3D reconstruction run at a resolution of 3 centimeters, exhibits many of the weaknesses of the Martian Cube's algorithm. The surfaces of the scene are very blocky and have imprecise geometry. The image on the right, taken from an offline 3D reconstruction run at a resolution of 0.5 centimeters, shows the effect of simply increasing the resolution of the reconstruction on the performance of Martian cubes. For comparison, the image on the left has 10,000 faces, and the image on the right has 9 million faces.
Any questions about the 3D reconstruction part of my presentation?
Okay. For example, I just have one question about 3D reconstruction. For example, I have two video clips of the same city, and the point cloud output of the two clips are overlapping, but not too much, but they are still overlapping. Can OpenArc can merge to point cloud into the same bigger city, bigger point cloud?
Yes, so I don't know if OpenArc provides this as a first class module, but there are solutions to your problem. If you're asking for algorithms that perform this, so the problem is called point cloud registration, where we take multiple point clouds and we try to combine them into one overall point cloud of a global space. If you want to hear about algorithm names, like iterative closest point is a very simple algorithm to solve this problem. Yeah, I don't have any slides on that, but that is my recommendation.
Okay.
My question would be about real-time dynamic scene reconstructions, because I think the sample you showed was a static scene. Would it be able to use OpenArc for dynamic scenes as well?
Unfortunately, no. So as I mentioned in the previous section for the other question, our SLAM system is built on a static scene assumption. And there's a very tight coupling between your SLAM system and your 3D reconstruction system. And if your SLAM system has a static scene assumption, it's pretty difficult and doesn't really make that much sense to try to deal with dynamic scenes in your 3D reconstruction module, right? You probably want to start incorporating a dynamic scene assumption into your SLAM. So no, OpenArc is a static scene 3D reconstruction.
I think if your scene has dynamics, that even the SLAM will fail, because you are doing localization and mapping, right? So, in fact, Adam also alluded to that the third part of his talk may be useful. One common scenario that, again, so I talk about autonomous driving. So autonomous driving, there's a lot of moving objects. You may know that in the solution for doing localization in autonomous driving, people extensively using landmarks. So you don't use feature points, you don't use stance points, because they all get, will be confusing you if you have moving objects. Over there, you will need to still have high confidence landmarks. They are not moving, such as the post office, mailbox,
or traffic signs. So in those cases, you will start with a SLAM algorithm that will be robust to dynamics, which Adam actually is going to talk a little bit about that on the third part of the seminar.
All right, thanks. That answers my question.
Okay, Adam. So let's go to the third part. Oh, there's a question.
Yeah, just one more question. So when you say the reconstruction part of OpenArc, so like you are already kind of doing 3D reconstruction when you do loop closure in a map. So does the 3D reconstruction part involve like densifying that map and then converting into a mesh, or is there also some other optimization involved on the poses like?
Yes, so the input to 3D reconstruction are the pose outputs of SLAM. I think the problem is if you don't have a separate pathway for 3D reconstruction, it's a little hard to convert just points. So if we think about our SLAM, right? Our SLAM keeps a map of the world. We have like frames, we have points in them, we have points that we're tracking, things that we think are salient features like corners of objects, but it's very hard to turn that into a mesh. And by mesh, I mean vertices with triangles, right? Like a model. It's very hard to turn that into a model. The benefits of, so what I talked about was a TSDF. So this is a different kind of data structure, and it's tuned to convert from our observations to an actual model. This is pretty important in order to achieve real-time reconstruction. But in terms of tracking, the 3D reconstruction module doesn't do much in the way of tracking.
So like it only optimizes the map, but does not like optimize the pose, the 3D reconstruction part of your system.
Yeah, so the pose optimization in loop closure is different from 3D reconstruction. It is a frame-aware optimization. So just comparing frames to past frames as opposed to a true understanding of the scene as a whole.
Got it.
Yeah, so I can also add that, for example, some of our collaborators from university other than Berkeley, they actually have tried to replace the brisk and the sparse feature components in the SLAM in order to improve the performance when you have no when you have repetitive features. If you have no features, then all bets are off for tracking, right? So, but if you have repetitive features, and the brisk is known to be not robust to that. And there are actually teams working on this problem by replacing the feature definition in the tracking part, but that does not affect the 3D reconstruction. You can replace the tracking part for the feature that you want that will be robust to repetitive 3D structures to improve the SLAM, but you can keep the 3D reconstruction based on the SLAM pose. They are separate.
Thanks for answering my question.
Yeah, Adam, so let's go to the third part of your talk.
I think Miyuki mentioned that, oh, sorry, we have more questions.
Yeah, sorry. Yeah, thank you for the presentation. I'm wondering that about the runtime part. Like I remember that you mentioned in your slide that the performance of the real time about your 3DR system and the SLAM. So I'm wondering that if you run both SLAM and your 3DR, that includes about all the backend systems and also the 3DR integration and mesh extraction, and also include the depth estimation part. What will be the real runtimes, like how much FPS you can reach, and on what kind of hardware you have? Yeah,
yes. So I can give you an example of what we used to do. We used to walk around with a Microsoft Surface Pro. We would walk around for, I would say, a runtime of around 2 to 3 minutes. Enough time to scan, like let's say 1 floor of a building, a family-sized house. And we were performing mesh extractions at 1 hertz and rendering at 30 frames per second. So the difference between, I guess, mesh extraction and rendering is only dependent upon your frame estimation. So I walk around, I take a step to the right, my mesh moves a step to the right. The mesh extraction happening at 1 hertz means we are generating a new model of our scene only 1 time per second. So for the second, you are going to be seeing like a delayed version of the model. I don't know if that's clear. But,
and you
yes.
said on what kind of hardware?
On a micro, so like a tablet. This has
Okay,
no
a
GPU.
tablet.
This is a CPU only system.
Okay, so, okay. Okay, got it. Yeah, thank you.
All right, so Adam, I think we can go.
Sorry, so Miyuki, I think, oh, sorry.
Yeah, so sorry. So attendees on site, please note that at 3:30 there will be a bus that will be taking you to the IMDA Pixel. Yeah, so if you're going there, the bus comes at 3:30. Yeah, thank you. Yeah, Adam, go ahead.
Okay, and I will move on to the final part of my presentation about object tracking.
A lot of work from the last year went into a new module for OpenArc, 3D object tracking. This is what I personally worked on with a team of around 6 students. We hope to incorporate this as an augmented reality module in the months and semesters to come. The problem we are focusing on is called digital twin. The goal is to track a real-life object with sufficient accuracy such that a virtual copy of that object, its digital twin, can be overlaid on top of it. This technology has different applications, from augmented reality mobile applications to industrial maintenance. Have you ever built anything out of Legos? Each Lego kit ships with pieces required for assembly, as well as a manual detailing each step with visualizations. With digital twin technology, you wouldn't need a manual at all. Instead, building instructions could be rendered onto a phone screen or a pair of augmented reality glasses directly aligned with the Lego bricks. How can we power digital twin? The solution that we focus on is called 3D object tracking. Object tracking answers the question, where is the known object in our scene? Known object refers to tracking objects that we know or have a digital model of. This is important as it allows us to develop algorithms that target specific objects. The where refers to the 6th degree of freedom, or 6th pose of the object, its position and rotation in 3D space. This problem statement is very reminiscent of the camera tracking in SLAM. However, the difference arises from what's being tracked. While SLAM tracks the position of a camera in a scene, object tracking focuses on the position of an object in the camera frame, regardless of the surrounding environment. Some of you might be familiar with 2D object detection. It's a similar problem to 3D object tracking, finding the position of an object in an image. Modern-day deep learning techniques, driven by convolutional neural networks and more recently visual transformers, perform this task with increasing levels of accuracy. Modern-day networks are capable of outperforming humans on image classification tasks on massive datasets such as ImageNet. However, when lifting this problem to 3 dimensions, it becomes a much more difficult problem. First, what we ask of the algorithm is inherently more difficult. Instead of just classification, position, and scale, the network needs to classify position in 3D space and rotate in 3D dimensions, arbitrary objects. The loss functions need to be carefully calibrated to achieve good performance, and object symmetries need to be thought of. Second, there is much less research on point cloud processing versus image processing. PointNet 2016 marked the beginning of deep learning on point clouds in a fashion similar to convolutional neural networks. Third, the datasets are much smaller. While ImageNet contains over 1 million labeled images, the state-of-the-art datasets for 3D object tracking contain fewer than 100,000 labeled images, coming from less than 100 unique environments. Fourth, annotating data in 3D is much more difficult and expensive. This is a major contributor to the third point. Following the themes of OpenArc, we approach object tracking through the lens of augmented reality. While a majority of the literature in 3D object tracking focuses on the problem as a robotic grasping problem, our augmented reality perspective raises some new constraints. First off, we need a solution that can operate in real time at 30 frames per second at a minimum. This is because a final digital twin product would require perfect alignment of real objects and their virtual counterparts in a video or a pair of augmented reality glasses in real time. High latency would lead to misalignment due to shifting object poses. Second, we have tighter error constraints. Robotic grasping has a higher tolerance for error, as minor inference errors can still lead to a successful grasp, and this is reflected in the metrics used to measure algorithm success. Thirdly, we require both textural and geometric alignment. This refers to objects that have geometric symmetries, such as markers, but have textural asymmetries, for example, a label that uniquely identifies the object's rotation. While the robotic grasping perspective to object tracking is more tolerant to predicting the position of an object up to its geometric similarity, incorrect textural alignment is an incorrect alignment for augmented reality. The current directions of research in the object tracking field include, but are not limited to, traditional methods and deep learning methods. Traditional methods tend to rely on key point matching, 2D and 3D computer vision techniques, but difficulties arise under harsh lighting conditions, sensor noise, and heavy object occlusion. Therefore, state-of-the-art techniques employ deep learning approaches to solve this problem. These deep learning algorithms can be divided into two groups, RGB-only methods and RGBD methods. RGB-only refers to algorithms that operate only on color images, while RGBD refers to algorithms that receive aligned color images and depth maps. The benefit of the latter is the ability to reproject the depth map into a colored point cloud using the techniques described in the 3D reconstruction portion of my presentation. A class of deep learning architectures beginning with PointNet has been developed to ingest these point clouds and infer qualities such as point-wise semantic segmentations and object poses. In our work, we focus on the third of these directions, deep learning methods utilizing both RGB and depth maps. These solutions offer the most promising results for algorithm tracking performance. Here is an example network, dense fusion, that was one of the pioneering works for RGBD object tracking. We start at the top left of the image where our input is an aligned RGB and depth image. We pass the RGB into a CNN to get color embeddings, and the reprojected depth image, a point cloud, into PointNet to get geometry embeddings. These two are then fused in a dense fashion, hence the name dense fusion, and a global feature is extracted. Finally, pose predictions are regressed using each pixel-wise feature containing a color embedding, geometry embedding, and global feature. In this manner, the complementary sources of data work together to create more accurate inferences. A general pipeline for 3D object tracking follows the procedure above. First, we process the RGB and depth data, either separately using their own backbone networks or in a more combined manner. Next, we perform pixel-wise semantic segmentation. Then, we take a region corresponding to an object in the image frame and predict the object pose, given the pixels and points within that cropped area. Different algorithms differ on whether the tasks of pixel-wise semantic segmentation and object poses are implemented as multitask learning in one network or in entirely separate networks. We will now dive into these different stages. First, many of you are probably familiar with techniques to process image data, specifically convolutional layers. Convolutional layers are kernels that convolve through an image and process data in patches throughout the image, taking advantage of the spatial locality of pixels. Depth maps pose a different problem. Neighboring pixels don't necessarily correspond to neighboring points, as silhouettes may divide large distances in 3D space. For this reason, most algorithms rely on point cloud processing networks that operate on the reprojected point cloud instead of the projected depth map for better performance. Inspired by 2D convolutional neural networks, what we are looking for is a network that can process 3D point clouds like their 2D image counterparts. The first property that a 3D point cloud network needs to satisfy is permutation invariance. 3D point clouds are an unordered data type, unlike images, which are ordered very naturally by the rows and columns of the pixels. We can think of a point cloud as a list of points and their features in any arbitrary order. A 3D point cloud processing network should be able to process a point cloud regardless of the order of the points given. Secondly, a 3D point cloud network needs to be robust to point noise and holes. Noise arises from sensor measurement, and holes are ubiquitous. Due to the nature of the point cloud coming from a single depth sensor reprojected, there is oftentimes no back or sides to an object, only the face directly facing the camera. Using features such as point positions, colors, and normals, the network needs to be able to perform tasks such as classification, object pose regression, and point segmentation. The two major categories of point cloud processing networks are point-based and voxel-based. Here is an example of a reprojected depth map. Notice the holes on the backsides of the objects. Also, notice the holes in areas with bad depth data. The first of the two major categories of point cloud processing networks are voxel-based techniques. Drawing directly from 2D convolutional layers, these techniques involve binning 3D space into voxels or cubes, reminiscent of the TSDF from 3D reconstruction. And after populating these voxels with the points from the point cloud, the entire voxel space can be convolved using 3D kernels in a fashion similar to 2D kernels convolving over 2D images. The downside of these techniques is their inefficiency when faced with sparse point clouds, so many of the voxels are empty. So point-based techniques have risen in popularity in comparison. Point-based techniques operate directly on the points that comprise a point cloud. Recall that points are an unordered list of vectors that contain elements such as position and more meaningful features such as color and normals. These techniques often use a combination of local aggregation, where each point gathers information about the points nearby it, followed by a downsampling step, where the point cloud is reduced in size. Performing these steps iteratively reduces the point cloud into fewer, more meaningful points. State-of-the-art solutions include PointNet, PointNet++, RandLinet, and point transformers. Recent research has been focused on building hierarchical processing structures, speed increases, and attention layers. These are some of the key operations performed by point cloud processing networks. First, the shared MLP, or conv1d, is a fundamental operator. The conv1d is a layer that takes in a single point and all its feature channels and outputs a single output channel. By stacking these conv1d operations side by side, we can create network layers that operate on a set of points with feature dimension A and output a set of points with the same number of points and feature dimension B. This is one of the fundamental operations for point cloud networks, as it allows us to perform channel operations in a permutation invariant fashion, since the layer looks at each point individually, so the order doesn't matter. Second, max and average pooling. Like their 2D counterparts, these operations take a group of points and output the max or average value for each channel over the group of points. This is oftentimes how networks incorporate information from a region into a single point. Third, k nearest neighbors. This is not a learned function, but a necessary component of many of the learned functions. It simply refers to computing the k nearest points to each point. Fourth, furthest point sampling. This is also not a learned function, but is often used to downsample a point cloud. It takes a set of n points and chooses a smaller set m of points, iteratively selecting the point in the original set furthest from the smaller set chosen so far until m points have been chosen, hence the name, furthest point sampling. This operation is used to uniformly generate downsamplings in an unordered point cloud. Finally, self-attention layers are beginning to see use as an alternative way to gather information at a point about its local neighboring points. Once we have processed both the RGB and depth data, we need to fuse them. Point Fusion 2018 and Dense Fusion 2019 first pioneered techniques to fuse data from the color and depth image. They passed the RGB image through a ResNet encoder, followed by a pyramid scene parsing network, or PSPNet, and the depth image through a PointNet point cloud encoder. They then take the encoded features for each point pixel and merge them together with their counterpart with a little bit of additional processing. These techniques were furthered by FFB6D in 2022, which used a bidirectional fusion module to iteratively fuse information from the color and depth images, leading to state-of-the-art results. By combining complementary sources of data, the network can extract more meaningful information. After processing the RGB and depth data, the network needs to perform pixel-wise semantic segmentation to determine which points and image regions belong to an object and will be fed into the object pose predictor. The benefit of performing this task using both RGB and depth data is the problem of scale ambiguity. For instance, the two pliers in this image are the same shape and texture, but have different sizes. Using only RGB data, they are indistinguishable, as a big plier further away from the camera is observed the same as a small plier closer to the camera. Finally, the points and pixels of an object are fed into a pose predictor that serves as the output of the network. Although the end goal is to predict the object's position and rotation in 3D space, directly outputting this leads to less than favorable results. Dense fusion proposed directly regressing a translation and quaternion for rotation, but required a process where the algorithm is iteratively applied to correctly output rotation. The non-linearity of the rotation space lends to this issue, requiring small rotations to achieve higher accuracy. Some works rely on the continuity of rotation representations in neural networks from 2019 to directly regress rotation, but in a more continuous fashion. A potentially superior output involves guessing the position of key points in 3D space. These key points are pre-selected locations on the virtual model that are evenly distributed throughout the surface of the object. Once the network has guessed the position of these key points, a least squares solver is used to estimate the highest likelihood rotation of the object given the key point relative positions. This technique tends to give better results, but requires a least squares solving step that slows algorithm speed. An even more expensive version of the key point parameterization is a dense UV parameterization, where the network infers for each point in the image where it corresponds to on the virtual model. A least squares solver is then employed again to estimate the object's most likely rotation. As with any deep learning problem, a large burden rests upon the data sets to provide large amounts of high quality labeled data. One of the major obstacles to 3D object tracking is the difficulty of labeling 3D data. While labeling 2D data is intuitive and fast for a human labeler, labeling 3D data requires operating on point clouds and usually involves a combination of human labeling and algorithmic assistance. One of the most ubiquitous datasets is the YCB video dataset, introduced by POSE-CNN in 2017. It consists of 21 common objects ranging from grocery items to tools, and 92 distinct video sequences of a configuration of the objects cluttered together. Each frame of these videos contains a color image and a depth map, and each object is labeled with its ground truth position and rotation, and each image is labeled with a per pixel semantic segmentation. Here are some current results from FFB6D, a state-of-the-art solution from 2022. Notice the high quality of the geometric alignment. The color points represent points sampled from the virtual model projected onto the frame using the object's inferred position and rotation from the network. However, the textural alignment is slightly worse for geometrically symmetric objects such as the Campbell's can, as it is a more difficult problem. Another drawback of FFB6D is the runtime, running anywhere from 1 frame per second to 10 frames per second on our computer with dual GTX 1080s. For our current work on OpenArc, we are focusing on improving these results through a combination of hardware and software means, achieving good performance at faster runtimes. Thanks to the students, both Masters of Engineering and undergraduate researchers, who contributed over the last year to OpenArc's digital twin module. Thank you for listening.
Do we have any questions for Adam? Yeah, we have not released the source code yet, so we are still in active development mode.
Our question is about the tracking. I think what we discuss is still just object pose estimation, but do you use any information when you track the object across the frames?
Yes, so I would say in our current work, we use the terms detection and tracking interchangeably. We just perform per frame object detection. So there is no semblance of like lifetime for these objects.
Okay,
But
so
there is a field of object tracking as well, where you do have an assumption of consecutive frames, but that's not our work.
I see. Okay.
Thank you. Yeah, so I had a question regarding like, so is this digital twin system going to be independent to the SLAM/3D reconstruction system, or do you plan to couple them somehow?
We plan to release it initially as a separate module that OpenArt provides. So kind of like how we have avatar tracking, hand tracking, SLAM and 3D reconstruction are kind of packaged together, and then object tracking is another module alongside.
Got it. Thanks.
So I will add to Adam's answer that the digital twin is I will say it's the polar opposite of SLAM. So in SLAM, you actually track based on the feature from the environment. Your environment can be cluttered, your environment can be unknown. So that is the problem with the SLAM. But for the digital twin, the number one, you start with assuming that you know the object. So when we train the neural network, actually the neural network is trained on the known object. So then when you see the same object in the environment, now the logic is that we disregard the cluttered environment. So actually the environment now is disregarded. So therefore, if you have a moving human or vehicles, as I mentioned to answer the previous question, you can use that as like a huge 3D sift. Right, so as like a Golden Gate Bridge, right? So you don't know San Francisco, but as long as you know that somewhere in San Francisco there's Golden Gate Bridge, as long as you see one object, and boom, you can solve for your localization. So that is one way that you can compensate for the environment dynamics. So on that aspect, the SLAM and the digital twin object tracking are counter opposite. They're actually not they are not complementary to each other, but they can complement in solving applications. But the algorithms are totally different.
Yeah, because okay, so the application is just interacting with this particular object. So yeah, you don't really have to create a map of the environment. You just have to localize this object correctly, and yeah, like it's deconstruct this object correctly, basically.
Yeah, it's a 3D version of Aruko markers for AR.
Got it. Yeah, thanks for the answer.
Thank you for the question. Are there any other questions? All right, so yeah, I think for Adam it's already past 3 o'clock in the morning. So if there's no more questions, I think we are happy to let him go. Thank you so much, Adam. Yeah, I really appreciate it. All right. So for the third part, we have a third contributor, Dr. Mohammed Khashavazi. But he is somewhere in transit because of his delayed visa issue. This is really, active of nature, so out of our control. So he was supposed to, meet with you guys and present his PhD work in its entirety in person. But since he's still in transit, but he's going to ISMAR, so you may be able to find him somewhere tomorrow. So you could actually look for, I believe that he's going to present his paper in the paper session. So if you want to get a hold of him and asking any questions, definitely I think you should be able to find him in the conference site. All right. So without further ado, so let me play his pre-recorded presentation for the rest of the tutorial. All right. So let me double check my sound. Okay, so let me double check it.
Hello everyone, it's great to be with you and welcome to the next part of our OpenArc tutorial at IEEE ISMAR 2022 in Singapore. I'm Mohammed Khashavazi, PhD from UC Berkeley. I'm an R&D consultant and strategist for metaverse startups in Silicon Valley and San Francisco Bay Area. The tutorial is a continuation of what we presented during our previous ISMAR tutorials, where we aim to share our main research elements in generative modeling and spatial computing. Today we'll be presenting some of the ongoing research we've been doing at the FHL Vice Center and XR Lab at UC Berkeley, and we hope to introduce methods that you guys can also implement in your applications or research in spatial computing. Okay, so let's get started. Let's get started with the term spatial computing. As you all know, spatial computing is kind of an umbrella term for augmented, virtual, and mixed reality modalities. The word itself can be described as computing in a spatial context, and it comes with a virtual and a physical component. The virtual component is the closest we can get to the concept of the metaverse. It's unlimited in space, you can go everywhere, you can virtually move around, and it's unconstrained physically from various surrounding built environments we have in our real world. The physical space, on the other hand, is pretty much constrained by contextual and functional requirements of our surrounding real world environment. And for us to develop a successful spatial computing application, we would need to address both the virtual and also the physical component of this modality. So when we're talking about spaces and everyday spaces that our spatial computing applications are going to be executed in, we should highlight the fact that there's much diversity in the geometrical and also functional aspects of our everyday spaces. Geometrical aspects such as size, layout, and material, and also functional aspects such as whether it's a workplace or it's a residential space, or even inside of residential space, whether it's a bedroom, kitchen, or whatever. Each of these target spaces which spatial computing experiences are supposed to be executed in have their own different properties and would need us to address and adapt to them. Yet, when we think about future AR applications, one of the main challenges that we can highlight is that there's somehow a design barrier between the metaverse developer and the users of the spatial computing applications. The idea that the developer doesn't actually know how its design or implementation is going to work in the target rooms. It doesn't exactly know the open spaces, it doesn't exactly know the boundaries, where the walls are, where the furniture is. And that makes it really hard for them to design a unique experience, or the experience actually they want for the target users, which are pretty much in an unknown space for the metaverse developer to experience. But this is not actually the first time we're having this problem, right? We've had this before. It's not only a challenge in 3D, it also was a challenge in 2D. The idea that a developer doesn't know or didn't know what target display is actually developing for, whether the end user is holding a mobile phone, tablet, or desktop. And the idea of responsive design aims to address this issue, right? So the fact that you write one code base and it automatically adapts to different display and screen sizes is the concept of responsive design, allowing the developer to have some kind of a communication between what it can be potentially designing for and what is actually developing in terms of its code base. Now, there's a lot of differences between 2D screens and 3D screens, and it's not really a similar, it might be a similar problem, but you can't use the similar implementation of responsive design and take it from 2D to 3D. 2D screens are usually rectangular, open spaces, open shapes, and our 3D environments usually come with obstacles, irregularities, and all much more complexities. So we can firmly state that this design barrier is something that we need to address in future AR applications. But it's not only the fact that one developer for large-scale deployment is having such issues. But actually, when we're talking about applications which multiple users are using in spatial computing context, the fact that each of these users are not aware of the other spaces is also a major issue, especially for telepresence applications. So what we'll be talking in this presentation and tutorial is sharing some techniques and methodologies we thought that can address this problem using contextualized spatial computing techniques in a generative approach. What we try to do is basically facilitate an adaptive process for spatial computing development. And in this regard, this presentation, we're going to talk about two topics. The first one on the left is about large-scale deployment for diverse environments, the idea of how can we come up with a technique or set of techniques that one code base developed by a metaverse developer can be basically augmented to a large-scale set of diverse environments. And the second one on the right is going to be how we can conduct telepresence from a spatial point of view in diverse environments. So let's start with the first one. And we can also look at this issue as a content augmentation issue. So when we want to do content augmentation for a similar space, for a sample space, we basically want to add an object to a space in its most simple way possible. So let's just say we want to add a sofa to this place. On the left you see a plan view, and on the right you see a perspective view. Hypothetically, the sofa can be placed anywhere in the space, right? As long as it's using very general rule of thumb physical constraints that it can, should be on the floor, it can go everywhere. The problem is you may have some conflicting and inconsistent issues with the context. On the left, you see the sofa is basically conflicting with the other geometry of the context. And on the right, you see that there's no geometrical conflict, but it's more inconsistent with the functional constraints that we usually hold within such rooms. So let's talk a little bit about the methodology. The way we looked at it was if we have a target room, the idea is can we turn that into a graph? And by graph, we want to calculate the bounding boxes of each room and have each of these bounding boxes as a node of this graph. And the edge of the graph would be topological relationships of positional and orientational matter. For instance, whether an object is in the middle of the room, is in the edge of the room, and also whether it's close to the other object or not. Also, object and room relationships, whether they're in a similar direction, whether it's facing other objects. And all these together would actually be represented as one single graph for each room. Now, when we want to add an object to a room, augment the content, we can initiate different graphs for this content augmentation criteria, right? And the goal of our workflow, the goal of our system is to find which one of these graphs actually come with the highest probability of scene plausibility, meaning that which one of these graphs would probably be a graph of a real room. The way we train this is basically by creating a knowledge model. We look at the Matterport 3D database and learn from graphs and input them in a knowledge model. The dataset, as I mentioned, is from the Matterport 3D. Of course, there's different types of datasets out there, from synthetic datasets such as SunCG, and also datasets that can be generated from computer vision tools to extract 3D bounding boxes from 2D images and so on. The reason why we use Matterport 3D when compared to synthetic datasets was the natural environments and the human actually correspondence of natural environments to synthetic data. And of course, at the time of this presentation, we felt that the 3D object detection or basically 2D to 3D bounding box techniques were still not in a position that we could have utilized for our large-scale training. So here's an example of the positional relationships and orientational relationships from the Matterport 3D data set. You can see, for instance, like on the right, the bed is usually, in most cases, towards the center of the room. You have storages that, mostly in the edge of the room or the center of the room. These are object-to-room relationships. You have on furniture-to-furniture relationships, for instance, chairs facing chair facing tables. And coming up with these relationships would give you some very probabilistic viewpoint of how objects are arranged in a general scene. So this is a very general workflow. On the left, you see scene priors coming up to the knowledge model. On the right, you see that sampling method that we talked about. For each furniture, we want to sample different possibilities, and the idea is, using a KDE model, we want to see which one of these graphs is highly plausible to be a real world space. So let's talk a little bit about our experiments. Here's a sample room, and we want to add basically a bed. This is a graph, and over here you see the probability map. The darker the result is going to be the higher probability, which would be the center of the object to be placed. There's also a probability map we're rendering over here in the orientation of the object, and as you see, the system calculates this would be possibly be the best location for an augmented bed for this room. Other examples over here, as you see, we see a living room augmented by a sofa, or a workplace augmented by an office chair, coffee tables, and also storages are all examples that you can see in this slide. Using this system, we can also do multi-object placement, basically placing and augmenting objects one by one. So if this is a target space of a room, which you see storage over here, a nightstand, and 2 sofas and a coffee table, if we want to add multiple objects, our system can do this one by one. And as you see, this is the probability map of each of these objects, a bed, a storage, and a sofa. And when we compare this to the ground truth, and actually what the data set holds itself, we kind of see some similarities and differences. In general, the location of these objects are placed in a different position and location, but you kind of see both of them are look functionally correct and probably plausible. So the fact that SceneGen isn't exactly augmenting the objects when compared to the test ground truth is the fact that it can be plausible, but it's not necessarily exactly in the same position of the test space. Here's other examples of multi-object placement. As you see on the left, they are partially empty rooms trying to be augmented with furniture. So let's get to our numerical experiments. The experiment that we conducted, as you may also notice in previous examples, is the fact that we get the ground truth, we choose an object, we take out the object, and then we give this scene and the object to the system, asking to do scene augmentation. And at the end, we compare the distance error between our scene augmentation prediction and also the ground truth. So here you kind of see the results of cumulative distance errors between the original position and the top position on the left, and also To make things more fair, we also calculate the closest top 5 positions for all predictions. This is basically ablation studies showing different components and different architectures of the scene-gen system that we describe in our paper. And at the end, we naturally chose the best architecture for our system using different components and also different relationship elements and constraints that we explain in our paper. For the user experiments, which we thought would be a supplementary to the numerical experiments, we came up with a user study that we reconstructed rooms in the Unity interface, and we asked participants to get engaged in our study in a way that the object would be placed in different types, and the user would basically give a rank of how it thinks this scene augmentation ranks from a value from 1 to 5. Now, for this to be a fair study, we showed the user different implementations of the scene augmentation. The first one is basically a random, which we call level 1. The second one is going to be level 2 of open random, so the object is going to be just placed in a random orientation in an open space. Level 3 is going to be scene gen, which would be our system working as its best. Level 4 would be scene gen with its height map, and level 5 would be the ground truth. So in this study, we'll be basically randomly showing each of these levels to the users and comparing how the users saw each of them. So this is our interface. The user would click on add furniture, and the furniture would be placed in the room. It would have a top-down view of a plan view of what it can see, and on the right it would have 2 perspective views. And on the top you can see from 1 to 5 it rates how plausible the added furniture is. So let's get to the results. It's very interesting that users, as expected, gave very low performance scores to level 1, level 2, which were random placements of the object. But when we compare level 3, which is our scene gen system, and compare it to the ground truth, you kind of see some very close similarities in terms of the Likert rating, and the scores of which the users gave. It's also interesting when we compare different furniture in our scene augmentation system. For most furniture, users rate scene gen and ground truth in a very close manner, except for objects like chairs, which you kind of see there's a very large range of scores, both in scene gen and ground truth. And of course, it's interesting to kind of think about it that chairs can be generally placed everywhere, and it's hard to really understand where a plausible positioning is or not. This other simulation, well, actually, this other plot also shows the top. I'm sorry, but I have to add more information on this slide, but it actually shows the top predictions of scene gen when compared to the top user preferences. So the idea of this slide is the fact that we asked the users after they did their Likert scoring to position the object in where they think it's the best position, and that would be the red points, and the green points would be scene gen's positions. For instance, in B, you kind of see that when the users wanted to add another sofa in the room, they gave 2 locations from their preferences. Half of the users one location, the other half the other location. And you kind of see that scene gen also predicts the same in its 1 to 5 preferences. On image C, a coffee table was asked to be added, and you kind of see also the different locations that SceneGen aims to add its prediction towards. So after conducting and developing SceneGen, we thought it's very important to show an augmented reality application, as it was one of the main components and concepts for this work. I'll show you guys a video. Okay, so as you see, this is scene augmentation in its manual mode. No systematic augmentation happens over here. It's generally like what you get in an IKEA app. You add the objects and you have to rotate them and place them correctly. But when we do a similar thing with SceneGen, we already have a heat map and the objects are placed in a potentially plausible location for the users to interact with and also adjust later on. Okay, so when talking about SceneGen as an example-based scene synthesis method, it's really important to also address the fact that one main element of success is the fact that what data it's trained on. This is a very general point of view that for learning data, we have very much diverse and high quality data sets for 2D interfaces, but for 3D, this is not the case. At the time of this study, when comparing synthetic data and scanned data, such as SunCG and the Matterport 3D, we had a lot of differences when comparing these two. The synthetic data of SunCG had more than 45,000 spaces, houses, and scan data sets of Matterport 3D only had 90. So we developed this system called GenScan of seeing if we can augment this data in a more sophisticated way. The idea of GenScan is if we input a 3D scan, if we take a fully scanned building as input, and by automating the parameterization of the architectural features of the scan, we can output alternative layouts of the same building. In other words, given one single scan, we can generate tens of alternative scans using our parametric data augmentation process. So how do we do this? In the first step, our proposed system extracts the floor plan of a given scan by utilizing FloorNet, a hybrid neural network which takes point clouds and 2D images from the scan as input and outputs a predicted vectorized floor plan. However, applying transformations on discrete elements of the floor plan can result in inconsistencies. So to address this, we develop and apply a parameterization function to allow wall systems to be continuous and avoid unwanted disconnected spaces. Each line element corresponds to a pair of nodes, and when a transformation is applied to the line elements, the nodes also change position following their corresponding line elements. From the floor plan extraction, we can predict the location of the walls and boundary elements of the room. And with that, by applying transformations to the parametric floor plan, its corresponding mesh walls can also parametrically follow the same transformation. Again, if we take a closer look, by only moving a wall, we can cause geometrical and topological conflicts with the furniture, as you can see over here. And therefore, to address this issue, we develop additional procedural models for the movement of the furniture cluster. We calculate the bounding box, and by assigning the bounding boxes to a corresponding adjacent wall, we're able to move the furniture clusters accordingly and avoid geometrical conflict. Using this process and applying transformations to the floor plan, we are able to generate a wide range of alternative spaces using a single mesh as inputs. To show examples of the resulting output, we apply our algorithm on real-world scan datasets such as Matterport 3D, which is captured by the Matterport camera, and also FloorNet, which was scanned using a Google Tango phone. So on the left you see input scan, on the right you see the manipulated alternatives of the input scan. In addition to mesh manipulation, our system also generates alternative texture maps for the augmentation process. To do so, we use a pre-trained style transfer technique to incorporate alternative styles into the current texture maps. We also apply various color tints to the transferred texture maps. And interestingly, by applying new texture maps to the mesh, as you can see in this figure, we can generate a wide range of alternative scan quality geometries and textures from just one single input scan. Okay, so with this challenge in mind, we had the idea of, can we improve the models we developed in our previous project in SceneGen for populating parametric 3D scan data sets. And so to recap, we train a model using scene graphs, and then we want to calculate the best plausible, the highest probability of a plausible placement in a set of sample inputs. Previously, we talked about how we use the KDE model, and as a further step, we developed a system that incorporates the parametric modeling called GSACnet. Now, GSACnet, other than the parametric augmentation, it also uses a more sophisticated architecture that we utilize, which combines graph attention, Siamese, and autoencoder networks for the scene augmentation task. So here's some examples of the bounding box manipulation of the sample rooms of the Matterport 3D dataset via GenScan. So this was basically using GenScan, the parametric augmentation of one single augmentation that transforms one single room to multiple data points. As you see on the top, it's just input of one room. The bottom is also input of one room augmented together. And here are some scene augmentation results for GenScan. Still, of course, this project is currently ongoing research, so not the best visuals and not the best renderings. But again, if we go with the same performance metric experiment of taking an object out and putting the object in and doing a distant error calculation, we kind of see that GenScan outperforms the state-of-the-art scene GraphNet scene augmentation systems in various furniture models. So to really understand whether GenScan as a data augmentation model can be utilized and have impactful results, we also did another set of experiments seeing which type of data augmentation method would facilitate and improve distance error results of scene augmentation. So here we'll just call the Matterport 3D dataset as mRegular. When we combine the Matterport 3D dataset with GenScan data augmentation, we'll call it MGS. Doing MGS with the area check, just making sure the room isn't larger than a proportional function, we call it MGSAC. And also using MGSAC and basically augmenting the data set by removing one object by each other, we call it MGSAC4. So as you see in this slide, MGSAC is actually outperforming the Matterport regular data set in both T1 and T5. And just as a recap, T1 is going to be the highest probability calculated by the scene augmentation system, in our case GSACnet, and T5 is going to be the best distance error or the smallest distance error in the top 5 probabilities calculated. Okay, so we talked about contextualizing systems for large-scale deployment for diverse environments. Let's continue our presentation with the idea of telepresence and telepresence in diverse environments. So I want to start by basically sharing an inspiring slide, which I was personally inspired in 2016. The work is called Holoportation. It's one of the early, not early, but one of the well-developed example of how telepresence can be utilized for collaborating with each other and basically meeting our loved ones. What I also always mention when sharing this slide is the level of realism the user experiences from the present standpoint. The fact that the presenter Shahram Mizadi actually takes one step back over here for his daughter to actually move around is personally very striking for me. The fact that it really feels his daughter is over there. It can be very helpful for next generation communication and really bring down the barriers of long distance relationships with loved ones, and also multiple factors in high-end workplace communication. Okay, so after looking at the slide, and talking about the inspiration, it's really important that we really look at how the system works and what are the constraints and what are the challenges this system has. If we pause the video for a second, we do see some critical issues. First of all, the amount of open space allocated for this experience in both rooms. So on the top left, you see the room where capturing takes place for the little girl, and the main screen shows the user space where the user with the headset is actually there. Both spaces are pretty large. I'm not sure if in everyday spaces we would be able to have this much large open spaces available for us. At least in our apartments in San Francisco or many other cities in the world, this cannot always be the case. The second factor which I want to highlight is if we look closely, we see some markers on the room. And this really shows that there's already been some level of calibration between two spaces. In other words, the developers of this experience knew what each space looked like. But as discussed before, the diversification of our spaces and a lot of privacy issues, accessing these spaces of each other's spaces may not be really feasible in everyday experiences. And if each time we wanted to manually calibrate our surrounding furniture for each telepresence experience, it would be very challenging, mainly with the fact that we don't know what other spaces or participants even look like. So it's fair to say, with our current real-world environments and surrounding, collaborative spatial computing has spatial limitations itself. And I actually want to open up this problem a little more. Let's say we have 3 users, user A, user B, user C. User A resides in this very large living room. You can see a perspective view on the left and floor plan view on the right of the large room or space which user A resides in. User B, however, wants to join the telepresence meeting from her small office space. And user C is working from home and is planning to meet in his bedroom space which is a little open area for others to join. So let's look at the first problematic scenario where spatial collision occurs when participants show up in each other's spaces. Let's see how. Okay, so this is user A's room, and as he's hosting the meeting, which augments virtual avatars of user B, user C, in an open area of this pretty big living room. If we hold the same positional relationship with each other between user B, C, and A, we kind of have problematic issues in other user spaces. In user B space, she actually sees no one, basically no one, because if you look at the floor plan view on the left, the other two users are located outside her office. You see when keeping the same positional relationships with each other initiated in the previous scene, they just don't fit in. And in user C space, there's more weird things happening, where user A is looking like a ghost stuck in the wall and the dresser, while user B is also colliding with the furniture. Both of these remote individuals and their avatars are in undesirable locations. So you may ask, why do we need to keep the positional relationship constant? Why can't we just, have each user have the option to force position and manually identify a desirable location for remote avatars to be augmented in its space? So let's actually see what happens. Here we have the participants holding constant positional relationships with each other in all rooms. Let's just allow them to manually force position remote avatars in their own preference. And here's the problem. When user A is looking and talking with user C in his own room, shown on the left, so let me say again, sorry. When user A is looking and talking with Mr. C, user C in this space is actually not being looked at. It's as if user A is looking at the wall in user's B space. And a more weirder thing happens in user C's room, that user A is actually talking to them, but in this basically positioning arrangement, which has been forced by the users themselves, it's as if user A is looking at another user. So the way we want to make sure is that this relationship, relational and positional this orientational and positional relationship is held within all users of the telepresence experience. So how do we address this challenge? The goal one is going to be to locate the maximum mutual space. The way we do this is we perform a semantic segmentation to determine the bounding blocks of each object of their room. And with this, we intend to locate the sandable spaces. Sandable spaces are basically the volume of the room in which no object located within a human height range is present. And the user movement can be performed freely without the risk of colliding with the object in its surrounding physical environment. We then calculate the sandable space by simply subtracting the area of which the object occupies in a room from the room itself. We do this with all the rooms. And next, we define a rigid body function G, where theta describes a transformation vector. So then we run a genetic algorithm, optimization algorithm, to determine the optimal theta of each rigid body motion. So the area of overlap between the boundaries becomes maximum. And if we map the mutual space back to the rooms shown here in the blue area, where all users stand or walk within the blue area of their own space, they are guaranteed not to cause virtual conflicts or line of sight mismatches within each other's spaces. Now, to add a little more flexibility and increase mutual usable spaces, we also define sittable spaces. Sittable spaces normally extend the standable spaces by adding areas where humans are able to sit on, such as sofas, chairs, and beds. Again, if we go through the same process, this time with sittable spaces, we observe larger mutual areas which users can stand, sit, and walk and move around in those spaces without worrying to cause any unwanted collisions in other remote rooms. So we wanted to implement our proposed framework on some real-world data sets just to see how it works. And We chose the Matterport 3D dataset for this, which includes a wide variety of residential houses and diverse styles and room functions. As you see here, the sandable areas are indicated in green and the non-sandable spaces are colored in red. And here, the sittable spaces are visualized in yellow. Again, green showing the sandable space and red being non-sandable space. Moving to identifying the mutual space between multiple rooms, this illustration shows how our genetic algorithm is gradually improving the results and expanding the mutual area and higher generation values. And here we show the mutual ground in blue after 40 generations of the search between these rooms. But then the question arises, what if we need more mutual space, right? What if it's just not enough and the identified mutual grounds are too small for the remote communication purpose? Say you want to play a game or inspect an object between the participants where the object doesn't fit the mutual boundary. What do we do? And that brings us to our second goal, which is rearranging the furniture so that we increase the mutual space while minimizing the overall effort to do so. And the effort of each move is basically calculated by multiplying the distance of the object's translation by the object's weight. In simple terms, moving a bed is considered to have a higher effort value when we compare to moving a chair for the same distance. So again, the goal is to slightly manipulate the room layout to increase mutual space with minimum effort. To simplify this process for the user, we define increased steps, where each step, the goal is to achieve 10% additional mutual space from its previous step, while maintaining the minimum effort to do so. Now, let's take a look at how furniture manipulation system works in an example. Again, we use real-world scenes from the Matterport 3D dataset for this experiment. We have a family room, an office, a bedroom. First, we extract the standable and non-standable spaces using the methods previously explained. Next, by utilizing our proposed mutual space identification method, we can locate the maximum mutual ground between the three rooms. We then use a strength Pareto evolutionary solver to run the optimization for the two objectives. So effort over here is shown in a vertical axis and the mutual area is shown on a horizontal axis. The mutual area on the horizontal axis, which we want to increase. So when we plot the rearrangement solution space, we can find the initial arrangement point on the Pareto frontier with the e-value of 0. Then by increasing 10% of area in each step, we find the rearrangement solution which satisfies the increased area goal and holds the lowest effort value in that step. And as you see, after 5 steps, we significantly increase the mutual space between the rooms while minimizing the effort required for the furniture rearrangement. Finally, to have a better understanding of how the users would experience the system's output, we deploy our method on a Microsoft HoloLens as an augmented reality application. For the target spaces, we scanned our office area and chose a conference room, a kitchen, and our main laboratory space for our experiment. We also provided the bounding box and semantic labelings for the model. The system then calculated the standable open spaces, visualized here in green, and the mutual spaces seen here in blue. Here you see the view from the HoloLens in the kitchen. We visualize the mutual space boundary with an offset of 40 centimeters of the ground so the user can clearly relate it to it. And here you see the main laboratory itself. Again, the blue area indicates that you can freely move around in this boundary without causing conflicts in the room. Finally, you see a floor plan view of the space with different screenshots taken in different locations of the HoloLens headset. So to talk about the limitation, of course, in our current version, the increase in steps may not have any continuous relationships with each other. For example, in step 1, you might be moving a chair in a certain direction to achieve minimum effort. But if you then decide to move to step 2, it doesn't take into account step 1's transformation. The next limitation is that our current system doesn't automatically take fixed position object into account and should be defined manually. We also currently use generic data provided by moving companies to estimate a weight of objects given its type. However, objects from the same type may have various weights, and therefore it would be important to integrate correct values to achieve more accurate results. And finally, for future steps, we definitely want to perform more extensive user studies. We definitely aim to develop this tool for a cross-platform AR/VR interface, and also use more robust floor planning methods for future manipulation. And with this, I want to thank you all for listening, and please feel free to ask any questions for our workflow. Thanks again.
All right, so I was just informed from the host that our session has ended. All right, so we just used all the minutes we have. All right, so I will just pass the control to our host. I don't think we have any questions, but as I said, Mohammed will be attending the conference in person, so you should be able to find him. And all our videos and tutorial material is on our website, vivecenter.berkeley.edu/tutorials. With that, I will thank everyone for attending today's tutorial, and also thank you for the host for their hospitality and all the assistance. Thank you.
Can you hear me all right? Yeah, this seems to be working. Good afternoon. My name is Dieter Schmalstieg. I'm from Graz University of Technology. Thank you so much for your interest in my tutorial entitled RegRug, a toolkit for situated analytics. So before we begin this, I'd just like to see, I assume most of you are in one way or another AR, VR, XR developers. Who's developing software or is working in a team with software development? Okay. Yeah, you don't have to feel inhibited. So what are you using for development? Maybe we can just hear suggestions. What is the platform that you're using for your development? Unity. Okay. Any other suggestions? No, that's great, because that's also what we will be using. This is some experience that I'm building on. But anyway, what we will do today is I will explain to you the toolkit that we have been working on, first from a more conceptual level, explaining the design rationale, and then we will do a little bit of a hands-on practical part. So we will demo a smart fridge. Of course, I brought a fridge to me to Singapore, so I will be showing you that. It's in my bag here. I promise you that. And we will then dissect this example, and we can take as long as you want. I have lots of material there, but maybe we will be at this point a bit more short on time, and we'll then lead over to a Q&A session where you can ask your own questions and learn a little bit about that. And I should mention this work is based on the collaboration with my PhD student, Philipp Fleck. And at the bottom here, you see the URL of the GitHub page of the project, where you can download all the materials that you would need to reproduce. I mean, the software materials that you would need to reproduce this experience and build your own Internet of Things augmented reality applications. And the hardware you'll have to provide, but I will argue how this can be cheap and inexpensive enough for everybody to do if you haven't got some already. To begin with, I should probably say what we're doing here. So RegRug is a toolkit for situated analytics. And by situated analytics, I mean bringing visualization and visual analytics applications into the real world by means of augmented reality. And for the visualization people, it's important to realize that we are not doing any new types of visualization here. So the toolkit lets you do visualizations that have been done before or design your own new ones. But in particular, it's about doing that in a manner that is easier than it used to be, in particular in an augmented reality scenario. So we do not break new grounds in terms of new visualizations if you don't count augmented reality visualizations as such, as a novelty. But we do break new ground in terms of what is really important, which is the interaction with reference. So reference are physical objects in our environment, pretty much anything that you can see or touch. And the visualizations that RegRug is producing relate to those reference in the environment. And there you have to distinguish two cases. One is passive reference. So for example, showing information on inanimate objects that are placed somewhere in the environment. For example, labeling. Labeling object categories would be one such use case. But then the other more progressive or more exciting category, if you want, is the class of active reference. So these are reference which have an electronic, digital life of their own, which are able to report on what's going on with them. And in particular, these would be Internet of Things devices, connected devices, smart devices, which send data at real time, at runtime, which should then be incorporated into the situated analytics experience. So for example, that leads to a visual change. And as I will point out, it's also important how we build these kind of experiences. So RegRug essentially is also an authoring platform at the same time. And it's a low-code authoring platform that borrows from Internet of Things practices to make it relatively easy and straightforward to create distributed systems, which then deliver situated analytics. And you can build all sorts of applications, including those that wouldn't even contain any visualization. You can make do with just the sensors, and then whenever the conditions are met, something happens. But of course, this is not what we're primarily interested in. RegRug in particular will take sensor data, deliver visualizations, and do so with a minimum of coding effort. And now I hope the audio will actually play through when I show you this video. Here we go. We can't hear the audio in the room, but we should. I mean, I can comment what you're seeing. That's maybe an easier fix. And let me jump back to the beginning. So I hope the people online do not hear those audio streams now. So this is a preview of the smart fridge example that we've built, but it's really only a toy example. You see two graphs here. One is temperature, and the other is the opening distance of the door. So there's a distance sensor inside the fridge, and now if you open the fridge door, of course the distance sensor hits, and you can see how there's a spike in the measurements, and the temperature inside the fridge also goes up because the warm air comes in, an alarm is displayed, everything is recorded for graphing purposes. If you think about these sort of sensor-rich environments, you can also go to your basement where there would be plenty of machines installed, like heating and power supply and so on, and they all have their own sensors and monitoring capabilities. And what our system is able to do, that what you see here, is it is detecting which sensors are present, looking up suitable visualizations for these sensors. So in this case, these are all just time series graphs. Also, you get panels that are dynamically synthesized, which show properties of the sensors, and the whole thing can be arranged in a convenient way around you in a sort of spatially registered way. So here's another example where we've built an sort of mock-up of the Museum of Pop Culture in Seattle, where they exhibit musical artifacts such as record covers, vinyl covers. And in this experience, a person is tasked with designing one of these exhibitions about the 1990s, my favorite musical period. Here you see an immersive analytics experience that is the stream system originally developed at the University of Constance, which we've recreated or rather ported over to RegRug, and the amount of code required could be cut in half by using RegRug as an implementation layer. So RegRug is also fine for immersive analytics, in this case parallel coordinates in 3D that were used in that experience. Where there's no reference involved, you don't have to have reference, but also the visual richness of immersive analytics systems can be duplicated. And finally, here's another attempt at replicating some work on designing musical interfaces. So in this case, expanding a keyboard with a wave shape editor, which lets you adjust the quality of the sound as you are playing. And there's no built-in visualization of that, but with using the existing knobs, but then a digital synthesizer, these additional capabilities, in this case affecting the sound, can be designed. So you see here, there's quite some variety of applications that we can build. And the main idea about using RegRug is to make it easier to build these kind of applications than you would with any of the existing toolkits alone. So if you work on Unity and you're probably using OpenXR or Microsoft Mixed Reality SDK or AR Foundation, one of these new libraries, they have a certain feature set that would not include anything that has to do with the physical world, maybe other than the hand tracking that is now native to the HoloLens, that would directly help you to address the non-virtual part of your application. And there's also other things that are lacking. And I've listed the requirements of the scope that we would like to cover, which I believe is fairly large, but it's intentionally at this, so it's composed like this, so we can deliver these visualization applications. And the requirements, I've numbered them from 1 to 6, would be, first of all, we want to deliver visualizations in augmented reality, or also virtual reality. We don't really have to draw a strong distinction there. The technology is overlapping enough. So deliver visualizations means the visualization should be visible or can be experienced by a user. The second requirement is that we want to create visual encoding for the purpose of visualizations in VR or AR. And as we will see, there is some work on that upon which we can build. So visual encoding means how do you create the graphics without designing them from scratch or writing from scratch code that produces some visual results. If you have a routine that draws a line, then of course by drawing many lines you could make a bar chart. Yeah? But of course other people have done bar chart generators before, so it's much more attractive to use something that is powerful and that will synthesize these visual encodings dynamically, which is what we want to do here. Then the third requirement is that the visualizations become context aware. At this point it's really a deviation from what existing software will let you do, because the existing software also for the AR space is mostly restricted to just 3D input sensing. There's hand tracking, or there may be some object tracking, but then it pretty much stops. Now the very recent versions of, say, ARKit or ARCore have some additional environmental sensing capabilities, like detecting planes in the environment or or detecting a dominant light direction, but it is very, very limited and not very suitable for this kind of smart device and Internet of Things scenarios that I've shown you. It doesn't go very far. And this is where we add a lot of infrastructure. And in particular, the infrastructure into which you can plug in new solutions that you may be developing yourself. Now, the fourth requirement is to create a comprehensive physical virtual model. And what I mean by that is essentially a digital twin. I'm not always using the term digital twin because it's a little ambiguous in terms of what is meant by that, too much overused in industrial product solutions. Physical virtual model means that we have a copy of the relevant aspects of the physical environment, also their semantics, in our application available. And again, the existing augmented reality toolkits will give you nothing that goes beyond where a table surface is in space. Yeah? That's really a minimalistic representation, and we need more for these kind of rich applications. The fifth requirement is that we want to make visualizations reactive to changes in the real world. So this goes beyond the former two, namely context awareness and physical virtual model. It builds on that in order to make it easy to define something that is adaptive to the real world. Yeah, this is the application logic that makes it easy for you to have visualizations, in particular, also other application behaviors that respond to changes that happen in the real world as the context changes or the physical virtual model changes. And we rely on reactive programming for that purpose, but I will expand on that later. And the sixth requirement is that we want to support the user in situated authoring of visualization. So by that I mean authoring that can be done while you're already at the target location and while the application is in some sort running. So you no longer, it's a continuous delivery mechanism. You do not, you know, what you do when you work for the HoloLens, for example, with Unity, the classic thing to do is you write C# code, you compile it, you deploy it on the HoloLens, and then you test it. And that's your cycle. Yeah? That's I wouldn't call situated authoring, because the authoring and the testing, or the situated testing, are separated into two phases. Yeah? And we would much rather not have to deploy explicitly to the HoloLens every time, but make a change and push it to the HoloLens immediately, or push it to the distributed system immediately. That may include server components and sensor components and so on, and continue the testing without interruption. And this is what we can do, unsurprisingly, but that has been considered by Internet of Things software developers already. And a big push here is that we're trying to take the strengths from that domain, adopt those solutions, and have that also available for this augmented reality development. In addition, I put here two non-technical requirements that I believe are very, very profound. They are actually aspects of the same thing. Do not reinvent the wheel. So we do not want to force you to adopt software that is created from scratch to demonstrate some academic goal, and then the problem of that, even if one makes it open source, is the maintenance of that software is very hard. Yeah? The amount of software that we are introducing new in RegRug overall is very small, and it's mostly reliant on existing components. And now comes the important part. These existing components are chosen such that they enjoy a strong user base, a strong community, and even commercial support to some degree. So it's very unlikely it will suddenly die of software age and then become unusable in a couple of years, because the software that in particular that comes from the Internet of Things domain, but also the software ecosystem of Unity, are very alive and thriving and will certainly be around for several years. So it's kind of safe to assume that these software ecosystems will be kept alive. And then since RegRag itself only makes it possible to use this software in a particular way, we're very safe in terms of future-proofness. And now, of course, I have to explain to you, after giving all these requirements, how they can work in practice. I'll start with the simplest one. How can we deliver visualizations or any other kind of visual experience in VR or AR? Well, if you've worked in VR, AR software development, you've probably used a software stack precisely like this. There's now commercial VR, AR, XR hardware, which could even be as simple as just a mobile phone, a smartphone, and or in other cases, an Oculus Quest, a HoloLens, whatever you want to use. On top of which sits Unity, which is the leading game engine, it's probably fair to say, in particular for mobile devices, and which excels by enjoying very wide support across the community, and designated plugins such as OpenXR. I should probably write the names of these toolkits, keep changing a lot. Also Microsoft Mixed Reality Toolkit, MRTK. These kind of libraries are essentially, we can view them as plugins for Unity that let us exploit what the VR, AR, XR hardware can give us. And then against these two software interfaces of Unity and of these XR toolkits, against these interfaces you can author your application, and this is what will let you do interactive 3D graphics. You do it as you would normally do for Unity, and with very little changes. By virtue of the VR, XR libraries, you get the sort of immersive experience for free. We are not using Web3D here. It's an alternative, but because in the spirit of openness, some people might argue this is the way to go. But at the moment, the Unity ecosystem for all sorts of XR is so strong that I believe it cannot really be beaten. That may change in the future, but then having another abstraction layer on top of building your application using another abstraction layer such as RegRag will only make it easier to port to another sort of implementation component. But anyway, now it's really about expecting it to be based on Unity. The second requirement was creation of visual encodings for VR and AR. And again, we did not want to reinvent the wheel, so we picked something that we thought was nice and working already, which is the Immersive Analytics Toolkit developed by Maxime Codet and co-authors. We have extended IATK, but we've kept the original design, which essentially is loosely following visualization practices around the grammar of graphics. So a grammar of graphics is designed to let you apply a sequence of rules, or if we're talking about software patterns, it would be a succession of decorator patterns in order to arrive at a certain, from raw data, arrive at a certain visual encoding. And then you can build these things as shown in this figure here, 3D scatter plots or 3D curve collections and so on. So for abstract data visualization, this is a very powerful approach. It's also reasonably fast because it internally relies on geometry shaders to convert the raw data into visual glyphs or visual artifacts. And speed is important if you either want to visualize larger data sets or you want to go to a mobile platform that isn't really all that capable in terms of graphics. And I'm afraid to say even the HoloLens 2 GPU is very disappointing in terms of performance. But for sort of medium-sized data sets and with this shader support that IATK introduces, that works reasonably well. Now, of course, mind that the way IATK was originally designed is that it lives inside the Unity IDE and the Unity integrated development environment, the Unity editor. And that would be the same kind of non-situated authoring that I've just complained about, where you first have to define your visualization on the desktop, and then you go off and run it on, deploy and run it on AR glasses, say, and that is when you switch medium and you introduce some complication. So we want to improve upon that. We have to give up the authoring inside the Unity IDE and move to an environment that makes that easier, and in particular lets you author not just the visual encoding from raw data, but the entire transformation pipeline of live data. Yeah, but the raw data starts its life at some point, but needs to be going through a collection step, filtering step. There's stuff that happens to the data before it's actually visually interpreted. And we also want to be able to author that, of course. And the last item, go beyond what IATK is offering in terms of built-in interaction. So this is reasonably nice with some filtering and brushing and so on. But that is certainly not the full set of interactions that can happen in an AR environment, because again, we want to include physical reference, physical objects, which is not something that is considered at all by any of these software solutions. But the important point here is, if you look at this software stack, the first two requirements are basically mostly addressed by adopting Unity, OpenXR, IATK. What we want to do is we want to concentrate on the remaining problems or requirements that have more to do with the physical environment and the Internet of Things. So how can we make visualizations context aware? Well, I mean, I'm specifically interested in Internet of Things. So we have sensors and embedded control systems that must be coordinated. And of course, there are strong solutions out there for that. Commonly, what is done is that a data flow programming approach or a data flow architecture is used. So what that means is events come into the system and are propagated in a graph-like manner, in a directed graph. And so you set up a graph consisting of nodes and edges, and these become pipes and filters. So the data is piped through the graph and filtered on the go. And this lends itself to a style of visual programming with node link diagrams that I'm sure you're familiar with, because game engines use it too, but they use it only for their internal software objects. And here we are interested in nodes that live in a distributed system composed of potentially a lot of a broad variety of devices. Of course, if you want to do more sophisticated data flow, then one idea is that you attach little scripts written in a scripting language to the nodes of such a graph, and these scripts implement the filtering functionality. So again, this is all existing. In our case, we rely on Node-RED, which is a very popular open source Internet of Things framework, which is based on JavaScript and Node.js. So it runs on some inside some software container or on an edge or cloud server atop a JavaScript framework, Node.js. And it executes a data flow composed of nodes and links that can be set up by the programmer. And Node-RED has a very large user community, which means there are many projects in home automation, but also in industry that rely on it and use it for either for tinkering, which is probably what we are doing in our experiments, also as researchers a lot, but even for larger scale sort of production environments. It's used quite a lot. And it has several features that are attractive to RegRug. So first of all, we use the visual programming based on data flow. These pictures on the bottom actually show screenshots from the editor. Java, so usually you have a headless server, but then it delivers via HTTP, it delivers this programming interface, so it can all be remote controlled on pretty much any device. So you see here in the software stack that we have Node-RED being based on Node.js as its runtime system, and an HTTP server that would, for example, deliver the user interface, but can also deliver other things, like you can query it for data that Node-RED stores in one of its backend databases. And about the MQTT and Mosquito part, I will talk on the next slide. But before I do that, I actually wanted to mention how Node-RED helps us in supporting a physical virtual model. So one of the things that most VR, AR, XR developments don't have is a proper model storage. The typical model of Unity is using file-based assets. You can either read files or load asset bundles that go through some sort of packaging mechanism, but these are basically static resources which are loaded and then converted into game objects that sit in memory. And that is not very suitable for this kind of dynamic environment that we want to support, where you have a distributed system with, data sources somewhere in a networked environment, and then processing that runs on intermediate nodes. That doesn't fit very well together. What you need to have is some sort of database mechanism where you can actually, at startup or even continuously at runtime, query what is out there in the physical environment. So for example, if we have this audience here and people come and go, and you want visualizations for every person that is present, like I'm wearing my AR glasses and I want to know who's there, and I get name labels or such a thing, then you would have to have a person detector, and the person detector would send an event when a person comes or leaves, and in the meantime, you have to store somewhere the identity of all these individuals, and that would require some sort of database. When a new person comes, you can look the person up in the database and you get the data that is relevant for that person. So we use databases for this purpose, and since Node-RED lives in a server world that is essentially very much related to a web stack that you would normally have. You see there's an HTTP server, and then there's additional tiers in a multi-tier architecture. So some of these tiers would be database tiers that run database instances of your choice. These can be SQL databases. We have primarily been using PostgreSQL, or non-SQL databases such as CouchDB, for example, which is a document-based storage. So that is where we store snippets of JSON mostly as data descriptors for these various phenomena that we have in the physical world. And these can be retrieved by querying via the HTTP server, which then goes to Node-RED and further onto these databases to give us this information. And there's nothing too surprising here. It's really the databases that plug into Node-RED that have been used already in pure IoT applications, for example, to collect the data or address queries that applications have that use Node-RED. That supports us here, rather than going through a file-based model as one would normally do in an AR application. So the AR application will also query Node-RED for data from the physical virtual model. And I'll demonstrate then a bit how that can be done. Another capability that we're relying on for creating the context awareness is a publish-subscribe architecture. So when you have various sensors that are networked sensors, of course, then you have to make them send their data to the destination. And the sensors will typically be small embedded processors that do not have an interface. And if you make them send data to only one specific address, then you need some mechanism to forward the data to where it really belongs. And this is exactly what a publish-subscribe architecture is doing. So a publish-subscribe architecture is a very efficient way of communicating in a distributed system where the communication is based on topics or channels, as it is sometimes called, which means the sender of a message, a publisher of a message, tags it with a topic, and then any number of subscribers can subscribe to a particular topic and will automatically receive any messages that are published that contain that topic. Now, in between sits a so-called broker, which routes the messages, and this you can think of this as like a server, but really it's only doing efficient routing. It is also the known point of contact. So, for example, you can have it listen to a known port on a known IP address in your local network, and that will let you establish communication between all the hosts that are connected in the local environment without having to hand out any IP addresses. Yeah, so that there's anonymous communication. The senders do not have to know the receivers do not have to know the senders beforehand, but the communication is rooted purely based on the knowledge and subscription to a topic. So one can establish a spontaneous end-to-end communication without getting a bit headache in terms of how the routing inside that network would work. And then this is of course combined by having a shared local area network. Typically we use one Wi-Fi, SSID, one Wi-Fi channel for doing that. And it is also very efficient. So the implementation that we're using is message queue telemetry transport, that's or MQTT for short. That is a protocol that was originally designed by IBM for their commercial message passing products, but has since then been released to the open source, and it's a protocol that is spoken by many sensors. Or there's sort of software adapters for other sensors. If you have, I don't know, competing standards like ZigBee, then it's possible to include that as well. And there's open source software such as Mosquito that acts as the broker. The speed of the protocol comes from the fact that it purely relies on UDP. So if you know the difference between UDP and TCP, TCP is connection oriented. There's a large overhead inducing latency in having this sort of streaming. Whereas if you have UDP, you only send individual packages, and of course one MQTT event fits into one UDP package, so it can just be sent around everywhere, and it travels very efficiently in this kind of shared channel network, such as a Wi-Fi network. And then Node-RED is just another subscriber or publisher on the MQTT communication bus, and it can pick any events that it wants, process them further, and feed them back into this distributed system. So now I've introduced the two main software platforms upon which we're relying, and I really I have only told you the existing stuff, right? But if you put them together, which is what I've done here, on the left-hand side you have a Node-RED-centric Internet of Things software stack that would run on a edge server, for example, some server machine. And on the right-hand side you have an augmented reality application using more or less the software that I have described before. If you put these two software environments together, then you already get a sort of sensor-centric visualization pipeline that can deliver sensor visualizations from raw sensor data in real time. And a visualization pipeline, if we look at this from a conceptual level, there's these 4 steps that are always required: the data acquisition, data processing or transformation, the visual encoding of the data, and finally the rendering. And all 4 steps are embodied here. We started the IoT devices, so of course the data acquisition happens by the IoT devices sending their measurements as MQTT messages to the Node-RED software stack. Inside Node-RED, some processing happens, some data transformation if this is desired. For example, the selection of the relevant data, which then gets forwarded to the AR application or AR client, as I will call it later on. There it goes into the IATK software framework, which does the visual encoding, so it produces a visualization representation as a game object that is then available for Unity for rendering. And then the 4th step, Unity is just doing the rendering and via its interface to AR hardware, such as, I don't know, a smartphone or AR glasses, it delivers this visualization finally to the end user. So hooray, we have a complete visualization pipeline that fits together in a reasonably nicely way in terms of expressiveness. All the things that I have mentioned so far can be done, but unfortunately with a rather mediocre ease of use. Now you need to learn 2 platforms, right? You've just mastered Unity and OpenXR and such, and IATK on top of that, which isn't completely trivial either. And normally you would just be loading some data and then visualizing the static data, but now you also have to learn how Node-RED works in order to make it send the data to your application. So we wanted to have a nicer solution for the authoring that is uniform across the entire platform. But nonetheless, just putting these software systems together, adding Node-RED practically addresses the 3rd and 4th requirement that I have. So you see we're making progress. We have this sort of world of Unity. IATK does the first 2, Node-RED does the second 2. What about question 5, make visualizations reactive? How can we make a nice user interface? Well, at this point, it's useful to take a look at sort of the theory of programming, and in particular the approach that is called functional reactive programming. So what is functional reactive programming? Well, you've already seen the data flow, and I'm sure you're familiar with data flow systems. And I would say, in a very casual way, I would claim functional reactive programming is a specialized form of data flow that lends itself particularly well to interaction programming. And why is that? Well, first of all, it's functional, which means you should not, and you must not have any side effects. And that is nice because it makes it much easier to develop a parallel or distributed system where you cannot have side effects propagating through the system because they would not be able to go from one node from one host in a network to the other, right? So if you have a functional program, it's kind of cleaner and can more easily be split into parallel or distributed parts. The second is it's based on event streams. So the original programming would use continuous functions, and the introduction of event streams rather than functional streams is beneficial because now you can simulate things such as state machines, for example. It allows you to have an interface that is more powerful, and it's still free from side effects because you can think of this from a theoretic point of view. You can think of this as a recursive function, a function that also depends on the previous state. So when you have some, let's say, some button which is pressed, then you know you can sample the button, so it says not pressed, not pressed, not pressed, not pressed, 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 then you release it and it's not pressed again. Or you only create events when the state changes, and you can convert one signal into the other. And it's much easier to write programs in terms of event streams, but it's still equivalent to a continuous function. And the final thing about functional reactive programming is that you make the application behavior reactive to these input events by basically starting something, a callback-like construct, whenever an event arrives, and it can change certain attributes of your program, and in particular it can change the attributes of a visualization. So functional reactive programming has been used in visualization before, in visualization systems, desktop visualization systems, or rather web visualization systems, such as Reactive Vega, for example, and it was found to be extremely powerful there. And we believe it's also the way to go for this distributed application development, because it makes it much easier to decompose your application into little nodes in this data flow, which communicate events and then locally react to these events. And the composability, I'm not sure if such a word exists, the support for composing software from smaller components is much more easily managed in this form of programming abstraction. So like I said, we want to have FRP as our, excuse me, our main sort of software abstraction. And that requires a little bit of an addition to our software stack here on the client side, where the first requirement is that ITK is made reactive, so the visualizations must accept events at runtime. This requires a little bit of a change of the way in which ITK produces its visualizations, because what it normally does is it receives the data and copies it one time to the GPU, where it's fed to the ever-hungry geometry shaders to produce the output. But now we have to selectively and lazily update the GPU side data structures in order to have a changing data set that is at the same time visualized by those geometry shaders. So that's a little tricky, but once done, we obtain something that is called reactive ITK. So when new data comes in, the ITK visualizations are now automatically updated. They are not exclusively updated when you make some brushing or one of these built-in interactions. They're also updated when new data comes in. The second thing is that we really wanted to have Node-RED-like data flow in Unity. And that means everything should be written in JavaScript. No more C#. That's a little bit of a radical decision, but everything that you have in C# can be wrapped in JavaScript, and that's also enabled by open source software. There's an open source tool, PowerUI, that is essentially a JavaScript interpreter for the for Unity, and so we obtain the ability to write JavaScript code to develop Unity applications. And now, of course, with that capability, we can enable a data flow that is compatible to Node-RED also inside Unity. Because what Node-RED is doing, apart from its visual programming interface and various tools, is it represents the data flow and simulates or runs the data flow. It executes the data flow. Executing a data flow isn't an extremely complex challenge. We do not have the ability to run Node-RED on the augmented reality client because it would just be too big and resource hungry. But making a lightweight interpreter for data flow in JavaScript from scratch and then interpreting a sort of a fairly fully compatible version of the Node-RED data flow on the client side becomes rather easy once you have the JavaScript interpreter on the client side. So what we get now is we can run data flow, JavaScript data flow on the backend side inside the Node-RED system, but we can also run an equivalent data flow inside Unity. So from a conceptual point of view, there isn't really any need to split this authoring in two parts anymore. You write one data flow that spans the entire distributed system. Some of the edges in the data flow would be MQTT, networked edges. Others would be local edges that are running inside one data flow process. But conceptually, it is all the same interface. And the only thing that technically that is missing here is the step 3. We connect the data flow to the reactive IATK. So we just make sure that there's no syntactic differences between doing things locally or globally. And now you have the opportunity of communicating from everywhere to everywhere. You can communicate between software objects inside Unity by sending data flow messages, or by going to the outside and send MQTT messages, and you have the same abilities from Node-RED. The only difference is what kind of subsystems are supported. So the IoT stack on the left-hand side here, for example, would have access to databases. The Unity application on the right-hand side would have access to, let's say, hand tracking that the HoloLens is performing. Yeah? If you want to feed in new events, then it would have to be with a local subsystem, and then it has to be routed to other parts of the environment. You cannot demand hand tracking in a Node-RED application in the backend. You would have to set up a network link in order to do that. But otherwise, it's a very, very nice abstraction that doesn't destroy the capabilities of the existing subsystems. You make everything in JavaScript, but if anything, this is rather more developer-friendly for people who may not be so seasoned in with compiled languages, and you have to learn only one interface for the entire system. So the 6th requirement, the situated authoring, is now in good shape. It's essentially solved by the previous measures. We have this uniform programming model based on functional reactive programming that runs everywhere. We can use the existing Node-RED editor for visual data flow programming everywhere. This is your development platform now. No more need to look at the Unity editor, the Unity IDE at all, because it has all been wrapped away in JavaScript and exposed to the data flow. And there's also additional user interfaces that are convenient to use for other parts of the system, such as for the databases, for example, CouchDB, Postgres, and so on. They come with their own administration interfaces, which are designed for exactly that purpose, for building and maintaining that database. Something that you wouldn't normally have if you do an AR application from scratch. And the final item is the hot loading of JavaScript at runtime. Basically enables the ability that you can debug and refine the running system. You don't have to shut everything down and then restart everything. You just have to reload a local data flow after some modification and can keep the rest of the system running. Or, well, I mean, you can also send in an event that it's doing some additional restarting. But in general, there's no specific deployment anymore, because what runs on the HoloLens is really a shell, if you want, or a bootstrapping code that is able to load a data flow in JavaScript that is pushed from the back end on the fly, and then that data flow is instantiated and scheduled immediately. So we only have to deploy new code on the HoloLens using whatever the Unity development and deployment tool when there's an upgrade on the sort of library that supports the JavaScript interpreter on the HoloLens. So, looking at the checklist again, it seems we have achieved all these 6 things now, like we wanted. In particular, we have the ability to be reactive to the real world by the extensions that we've made on the client, in particular the reactive IATK, and we can support night authoring with the Node-RED editor. And this is what the what the RegRug software system is trying to achieve. And now, for the rest of the time, I would like to switch gears a little bit, but maybe it's time to make a short break or have time for some questions. Any questions so far? Okay, then I propose we make a 3-minute break before I start with the second part. Okay, so after this very short break, I would now try and show some very daring live things. In particular, show you the smart fridge. And to remind you again, what is the smart fridge doing? The scenario that we're trying to address here is that we have a fridge that has been extended with sensors. That's a real thing. I mean, we made that by ourselves, but I know that, for example, in medical practices, you must have a monitor for the fridges because any like loss of temperature could make the medicines and vaccinations go bad. So we show these graphs in augmented reality for the fridge, and then there's this alarm mechanism. If the fridge door remains open, a sound is played, an alarm text box is shown, and the whole thing is, of course, recorded. And the data comes from sensors which are measured in real time, so we're going to need a sensor pack. The sensor pack itself is not something that I will describe in detail here, but it is based on a node MCU that contains an ESP8266 processor. So this is a very common maker type processor, and to which we have attached two sensors, a thermometer and an ultrasonic distance meter. And I have one here. Unfortunately, there isn't a desk, so I have to improvise a little bit. So this is the sensor pack containing the electronics that you see here, which will cost a few dollars to get. And then on the Node MCU, we run some firmware that has a nice interface, Tacoma firmware, which is also open source, highly configurable. And this is just a cheap and convenient way to get started with this kind of thing here. But you could have any number of sensors of any fabrication as well. And network connectivity is achieved by Wi-Fi. So it will connect to a Wi-Fi and then be remote operable and can be managed remotely over a Wi-Fi link with an HTTP, with a web interface. This is our sensor. The distance sensor of the thing points towards the door. If the door is open, where in our fridge setup that you see here in the picture, we determine the threshold of 35 centimeters, and if the distance reported is larger than 35 centimeters, then we assume the fridge door is open. So this is the scenario. And then on top of that, there's the visualizations, which are made with IATK. There's two time series curves being plotted here with some color coding. Essentially, it's just flat, so 2D visual encodings here, which are placed in 3D space at a location that can be determined either statically or can be taken from some form of a physical virtual model that is stored in a database. So here you have this behavior that the x-axis is the running time series, y-axis shows the data point, or the offset on the y-axis is the data point of either the measured temperature or the measured distance. So this is a visualization that we built in IATK that is very much like other visualizations that have been built with this tool before. And now here's what it looks like. So you see the curves on the fridge. Now this is filmed from the HoloLens output, and as soon as you open the door, you get the alarm. You also see the spike of the distance, which is on the left, and now, of course, door has been closed again and the alarm disappears. So this is the kind of experience that we want. What kind of hardware did we just observe? Here's a diagram that shows this conceptually. So we have all the components connected with a Wi-Fi router. You have the sensor pack on the left-hand side. You have the back end that runs Node-RED and MQTT in particular, and you have the front end, which in this case was a HoloLens 2 running our Unity application with IATK and JavaScript. Of course, I didn't bring a HoloLens. If I did, it would not be possible for you to see, and also I don't want to bring a HoloLens through Singaporean customs. So I did this instead. I brought the Node MCU. I also brought the Wi-Fi access point. Here's my Wi-Fi access point. It's really neat how small these things are these days. And I'm going to plug that in now to boot it up. So I'm only plugging these devices into my laptop to get USB power. Now there's no data connection going on here. And then the things on the right-hand side, I will sort of simulate with my laptop. So what I'm going to do is I'm going to start the whole back end in a virtual box running an instance of Linux. And I will run the front end inside the Unity IDE rather than deploying it on a HoloLens. But I would like to emphasize that the Unity IDE builds for Windows Universal Platform, and the same code would immediately deploy on a HoloLens as well. So there's no cheating going on here, just sort of valid simulation steps. Yeah, and the Unity IDE and the VirtualBox will actually communicate via the Wi-Fi router, so everybody's on the same sort of network level. Okay, and now I have to follow my own cheat sheet for running this demo. So what I did in the background already is I started the Unity IDE. There we are, where I've loaded the RegRug project, the front-end or AR client project, but I haven't started it yet. I did that in advance because the loading sometimes takes 5 minutes. Unity isn't super efficient in loading projects. And now I have plugged in the Wi-Fi router, so we should have an extra Wi-Fi now. So now what I'm going to do is I'm going to join my Wi-Fi. There we are. Okay, great. I'm always worried about this step because there's 5 different Wi-Fis, and if they're competing for channels, then that can be flaky. So it takes a bit to do that. But in the meantime, I can plug in the sensor pack, power it up, again, just for power. And what the sensor pack will do is, once it's turned on, then it will automatically connect to the Wi-Fi access point. And now I have to test the sensors. I wasn't expecting a hand mic, so I have a little bit of a problem with too few hands here. But I can do it with one. So I'm going to a browser now. And I'm connecting to the sensor. That's not so good. Let me try to unplug the sensor pack one more time. I have to say that I've never shown a demo that complicated before and for an actual audience. Oh. Wrong. That was the wrong address. That's the reason. Yeah. Ha. Ta-da. Okay, so here you see my sensor pack. You see that now the fridge door is closed, and in the 5th line it says distance 4 point something centimeters. My hand is the door, okay. Now I'm opening the door, and the measurement is 200 centimeters. Yeah? But I mean, this is not RegRug. This is just the Tacoma interface that runs on the sensor pack with the embedded web server. I can also demonstrate to you the temperature, which is now 23 degrees. So let's see what my biotemperature is if I have COVID. Okay, you see I get it to 30 degrees or so. And of course, if I turn it face down, then the door is also virtually closed. But that's only half of the story. Now I have to start the virtual machine that runs the backend with RegRug. And here's my virtual machine. So it's inside VirtualBox 6.1. They just released version 7. I dare not upgrade because it will break my demo. But other than that, it should be fine. So this is booting a Linux with all the RegRug, well, the Node-RED components in Docker containers, nicely arranged inside that virtual machine. It also runs a desktop, but I'm not interested in the desktop because we do everything with the web interface. So I'll show you the web interface. And this is this other link that I erroneously tried before. This is the Node-RED visual editor, and this is not showing the right flow because it's showing the, I don't know, these are sorted alphabetically. But here's our fridge flow. Yeah? It may be a little difficult to read at this resolution, but this is the nodes and filters editor that you have here. And now if you go to any of these nodes, where do I have one? So here, for example, you see JavaScript code written for Node-RED that is attached to one of these nodes. And we can discuss some examples for that. So this is basically the API that you're using. But then the overall program structure is mostly not based on what you do here, but it's based on how you compose a graph from various nodes that perform actions on the events that they are processing. Now I'm going away from this view, and instead, because the backend is running, I'm going to call up the I'm going to call up the regrug backend user interface, which looks like nothing, but it lets me choose the code that I want to run on the AR device. Yeah, so I've selected this Fridge 2 project to run on the AR device. And now all I have to do is start up the AR device, which here lives inside my Unity IDE. So this is starting kind of slow. So to recap, I have just started the regrug sort of player on Unity, and now I'm going to push the code that's supposed to run inside that player from my backend to the Unity client by, well, essentially this button here, which is triggering a function inside Node-RED that we have implemented to send this code via an HTTP link to the regrug software on the mobile device. Yeah, so and now, yeah, now I have my smart fridge visualization running here, and to prove that it's actually doing what it should be doing, I'm going to. We don't. Let me just see if we have the audio now. Probably we have. So I'm going to open the door. Ta-da! There's the alarm. And you should be hearing an alarm now, but for some reason we don't. Reason is that I don't have headphones. So here's the really annoying alarm for you as well, and as soon as I close the door, it's gone. Yeah. I mean, obviously for this trivial example, we could do a much easier way of putting everything together. But what regrug will let us do is it will let every part of that system scale up, right? We are running a full backend, we have databases, we have publish subscribe for getting the sensor data in, we have a visualization generator, and they all fit nicely together. Yeah, so that's the live demo. And what I will now continue with is looking at some of the ingredients of building that practical example. And we are also in the process of writing this up in a more concise handbook that helps beginners use that sort of thing. So just to give you an impression of what kind of coding activity or authoring activity is required here. This is the totality of the smart fridge implementation. I mean, it's a rather full slide, but bear in mind, this is mostly boilerplate code that is taken from some templates. I'll show you that in a second. So these structures are very repetitive, and it's just that Node-RED displays them all. But the logic is relatively simple. So we have a few groups of activities. The first is the deployment. That's always the same. That is the ability to push the data, the code to the client. Then there's setup of data sources, setup of visualizations. The visualizations that are no longer set up in the Unity editor. The ITK visualizations are no longer set up in the Unity editor, but instead they are set up by creating a series of decoration steps as a Node-RED graph. So there's two of them: the temperature visualization, the distance visualization. Then there are the actual sort of read the data from the network and and deliver it to this alarm mechanism where there's a few lines of custom code that produce an alarm box. And then the final part is the visualization update. So this is really just data transformation where data is taken from the real-time sources. You can see how the data goes in here. It's processed a little bit, and then it goes into the visualization part, into the sort of input data structures of IATK. Yeah? So most of this is just getting data to the right places, and most of the nodes don't even have any procedural code attached to them. Plus, we create a library. I mean, we're in the process of creating a library of templates, for example, for setting up a line graph, that's the top thing, or for connecting to a real-time data source over MQTT, that's the bottom thing. And these node groups are always the same, and you only have to enter a few parameters to make them do what you want. If you actually want to use Node-RED as a development system, then normally you wouldn't use the virtual box. You would be using a dedicated Linux machine that is permanently on the network, because that's easier for development. And you install Node-RED just as an application, and then Node-RED has its own package manager. You can go to this URL, for example, to bring in the whole toolkit into a Node-RED installation. So here's just a few glimpses at the various portions of the smart fridge. I'm not expecting you to understand all of that. I just want to convey some feeling of the complexity of the implementation. Yeah? So what this is doing is, not sure if you can read the text on this. These are all, of course, screenshots, and when they go through the projection, it's a little hard to see. But what is happening here is that a real-time data source is created inside IATK, which now has these various dimensions, and the dimensions are temperature and distance, for example. Huh? So what you see here is that these are all nodes that come from a node palette. They are predefined. You just have to plug them together and insert, for example, the name of the sensor source, like temperature here. Then there's the visualization. This is basically going through various stages that IATK is expecting, and you don't really have to build the IATK configuration all in code, but instead this is all sort of prepackaged sensors with a few exceptions. Yeah? So the code is here for set all attributes. What that is doing is it's initializing the data structure to the number of data points that the graph should have. The graph can have a variable number of sort of entries, and the number of entries that we want is being pushed here. So this is why you see a loop here where things are written to basically the data structure, which then goes on the GPU to feed into these geometry shaders. And the second thing here is this allow manipulation node, which is essentially adding what's the name of this? A collision box, so that the data can be grabbed and dragged around inside Unity. Then there's the live data storage part. So what is happening here is that these MQTT nodes provide the input. What you see here is it says telemetry /something/something/something. So oftentimes you arrange the topics of the publish subscribe in a hierarchical manner, and then you can also use wildcards like the star to subscribe to everything that is, for example, under telemetry /something. Yeah? So this is what is happening here, that the sources for this and for the MQTT are set up, Then the next node, the orange one saying pass, is reading the JSON representation that comes inside the MQTT container and is creating a JavaScript data element, basically just a variable from that. And then here you see how this branches out into the alarm branch. The alarm branch is really just an little sort of local state machine was implemented with if then else, which says if we had an alarm the last time and the door is still open, continue showing the alarm. If there was no alarm last time but now the door is open, then show the alarm for the first time and otherwise hide it. Yeah? And then this the data also goes to what will be shown on the next page. So here this is a real-time data source get. This is how we're going to feed the data now into the IATK software package. And here is the visualization update. So you see here the data sources go into the distance and the temperature go into this IATK feeding graph, which first copies the data to IATK, and then it assigns the data to these various, they are called dimensions in IATK. These are the data structures that IATK is using. So this is really just a controlled way of copying over the data into IATK, which is always the same unless you want something special applied. Like, I don't know, if you want a normalization of the data, you would have to run some code that does normalization here. And here you get all the various dimensions or the data attributes, so to speak, that IATK has available, and you check the ones that you want it to go to. So, I mean, overall, this is a very small amount of procedural code that has to be written to arrive at this sort of experience here. I guess now would be a good time to stop. There's, I also have instructions how to set everything up on your own machine, for example, but the problem with that is I tried it with another group. So first of all, you haven't brought the hardware to do it. I mean, you see a laptop is basically sufficient. We could all use the same Wi-Fi access point. I don't have a sensor pack for everybody, but then you would have to download several gigabytes of software and install it to get started. The software is all free. So that's very nice that there isn't really anything that would at least academic researchers keep from using this. You can use Unity. I mean, you are already doing that. IATK, RegRuck, Node-RED, these are all open source software packages. The sensor box costs you $20, not more, including shipping. Probably here in Singapore, you may be able to get it on some electronics market. I don't know. So there isn't a big hurdle to get started, but the software, including Visual Studio and Unity and VirtualBox and everything, is multi-gigabyte, and it takes probably 2-3 hours to install everything from scratch. I tried that with another tutorial group, and that part was the sort of tedious part where we went to drink a lot of coffee. So we're not going to repeat that today. But otherwise, I'm happy to help you get started, either now, answering your questions, or also reach me online and let me know what you're up to. Thank you very much for your interest, and I hope you want to use RegRuck. Any questions? Yes. Yeah, where is stuff in space, and what does it have to do with the, how did I put the graph on top of the fridge? Yeah, yes. So you have to have either, you have some trackable And this is something that would come from, for example, we've integrated the Vuforia toolkit, which detects visual fiducial markers, and then you put that into your Unity project. It creates events which are then sent to to the Node-RED, and this is how you would make the graph appear on some fiducial marker, for example, or on some trackable object. Or alternatively, what you've seen in the videos, but of course not in this sort of tracking-free Unity local installation here. There was no tracking running, right? What you do there is you store the position of all the visualizations or all the elements that you want to have. Yeah? You create a table in your database saying where in space you want them to be. We have a tool where you can point to a location and then it just stores that location, yeah, and you give it a name. That's not very sophisticated, but it's already doing the job, and it means the same application or the same experience can be deployed in multiple rooms or multiple environments simply because we have the database. The relative position would always be relative to some starting point, so there's at least two ways for doing that. Either you use the Azure world anchors that come with the HoloLens if you're using HoloLens. Apple ARKit has the same mechanism, and also they all have world anchors. Yeah? All these SLAM tracking systems have world anchors that let you recognize a place, and then you get the same coordinate system again. Or you combine it with some fiducial marker where you say the origin is the fiducial marker, but the fiducial marker is, I don't know, glued to the fridge or glued to the wall. And that's actually the most reliable way of doing it. The world anchors work but can be subject to drift over time. So the main thing is you need to establish world coordinates, and you need to establish at least a rudimentary physical virtual model in order to have things that are in a meaningful place in the world. The alternative is you don't have a meaningful place. You spawn it wherever you're looking at the moment when the thing is ready. I mean, that's also a way of doing it. Then it's just in front of you, right? It's not a very pretty approach. But you could, for example, have a heads-up display in which a 3D visualization runs. So as you're moving, it would always be 1 meter in front of your nose. That's yet another way of doing it that can make sense in certain applications. More questions? Well, if not, I'm available for the rest of the week. If you are interested, please just reach out and I'm happy to talk to you. Thank you.